No eres el único. Sí, ok. ¿Listo? ¿Sí me escuchan? Ok. Buenos días, ya vamos a comenzar la sesión de la mañana. Sí. Ok, estoy hablando para... Hola, hola. Hola, hola, hola. Hola, hola. No, hola. Aquí está la... Está encendido. Hola, hola, hola. Hola. Todavía no se escucha, ¿no? No se escucha. Ok. Pero acá no escuchan, entonces arreglando el volumen. Estamos arreglando el volumen porque no. Ok. No se oye. Si no, otro micrófono. Faltan los micrófonos, por cierto.
Acá sí se escucha bien.
Faltan los micrófonos portátiles. Ok.
Acá escuchamos bien.
Hola. Muy bien. Uy, ahora está fuerte. Buenos días a Morelia, Puebla, Ensenada y CEU. Entonces, vamos a comenzar hoy con NIRSpec Multi-Object Spectroscopy. Esta es una presentación de 1 hora, realmente especializada para la gente interesada en este modo de observación. Entonces, si no saben si están interesados, pues ponen atención las 10 primeras transparencias y luego pueden hacer otra cosa si ven que no está padre. A las 10:30 vamos a tomar una foto grupal. A las 10:30 es en 1 hora. Hay como que un sonido desagradable, ¿no? Cuando hablo. Ahorita lo arreglamos. Entonces, 10:30 no se vayan para estar en la foto, por favor. Creo que ya lo arreglaron, el sonido. Y después seguimos con Wide Field Slitless Spectroscopy. Muy bien, entonces comenzamos. Voy a asumir que me escuchan en las sedes remotas. Muy bien, entonces, so what is multi-object spectroscopy, MOS? It's an efficient way to obtain the spectra of many sources, all within the field of view of an instrument at a single pointing, so simultaneously. And by the way, I just updated these slides. So if you downloaded them yesterday, you are going to have to download the updated version of this presentation. Okay. So there are 3 instruments with James Webb that enable you to do multi-object spectroscopy: the NIRSpec Microshutter Assembly, MSA, the NIRS Wide Field Slitless Spectroscopy, and the NIRCam Wide Field Slitless Spectroscopy. Now, you may wonder which one is the best. So there is a JDocs article on the microshutter array versus the wide field slitless spectrographs. To find it, you have to go to Proposal Preparation, the menu on the right, Methods, Roadmaps, MOS Spectroscopy. And some of the differences between these options are the field of view, the wavelength coverage, and the spectral resolution. So in this presentation, I'm going to focus on NIRSpec Microshutter Assembly, MSA. And this observing mode is able to obtain spectra of hundreds of objects simultaneously within the 3.6 arcminute by 3.4 arcminutes field of view of NIRSpec at the same time. No está la presentación. Entonces, la intenté subir y falló. La voy a subir al ratito, ¿sí? Disculpen. No van a tener que seguir una actividad. Entonces, creo que no es problema. Muy bien. Entonces, here's the image of, let me turn on this pointer. Here's the image of the NIRSpec Microshutter Assembly. So it is a 4-quadrant array of tiny configurable shutters, little doors. The entire array has 250,000 shutters. And each shutter is just 200 by 450 milliarc seconds in size. And you can open them or close them with a magnet. Okay. NIRSpec has 2 detectors, which are highlighted by the red squares here. And there is a gap of 20 arc seconds between these detectors. And so the spectra disperse from left to right across the detectors. And depending on where you are in this grid, maybe your spectral trace will fall on the gap. And there are dithering strategies to fill in the gap, okay, in APT. All right. And just so you know, here are the fixed slits, which I talked about yesterday, and I'm not going to talk about now. And the NIRSpec IFU is there. Okay, what's special about NIRSpec MOS Science is that it is a 2-step process for the submission. So these two-phase process is due to the very tiny shutters in the MSA and the need for precise target positioning in them. There's an alarm sounding. Is that a matter of concern? No. Okay. So after proposal submission and acceptance, an aperture position angle assignment is made by the Space Telescope Science Institute. Okay. And by the schedulers of the Space Telescope Science Institute, so that the NIRSpec MOS observations can be scheduled more efficiently and flexibly. Okay, so you do not select your position angle for the NIRSpec. Okay, it's going to be assigned to you by STSCI. Okay, and so hopefully the field that you want to observe is more or less symmetric, and you will see how you plan and what you submit during the first step before you receive your aperture position angle. Now, I want to tell you about the MSA planning tool, MPT, which is one of the tools in APT. MPT was designed to align a set of science sources within the very small microshutter arrays, and it's right here. Okay, this is used only for NIRSpec multi-object spectroscopy. Okay, so more on the first phase of submission. So in the first phase for proposal submissions, users will typically run the NIRSpec MSA planning tool that I just showed you to create a set of planning visits with placeholder pointings and MSA shutter configurations that will be representative of the pointing and configurations after the angle, the aperture position angle has been assigned. And so provided that the source density is representative, MPT can predict the number of targets to expect for each pointing for a given observing strategy. So for proposal submission, the phase 1 of the proposal submission, it is important to include any fully specified NIRCam pre-imaging observations that will be used to locate targets for NIRSpec follow-up. And I will talk more about this. Timing links should be included to ensure that NIRCam pre-imaging is carried out before NIRSpec observations by a sufficient margin. This is done in special requirement sections of APT. NIRCam pre-imaging, NIRCam is a different instrument from NIRSpec. NIRCam pre-imaging is only needed if you don't have a good enough image already that provides the accuracy that you need to place the sources in the microshutters. Then there's the second phase, and the second phase begins after you have received your aperture position angle assignment and after the NIRCam imaging is obtained, if any. And then within a few months prior to the first multi-object spectroscopy observing window, users will again run MPT, which will utilize the latest MSA shutter operability status, the assigned APA, and to design the final MOS observations that will specify the exact pointings and MSA configuration and the expected targets that will be observed. And this is called the program submission or the program upgrade. And the reference stars used for the target acquisition must be finalized in this submission step. So a typical multi-object spectroscopy observer with NIRSpec will use the MPT, the tool on APT, to create optimal plans for MOS observations that attempt to maximize the number of observed sources. In order to clarify the MOS planning process, a step-by-step roadmap for proposing NIRSpec MOS science is given in JDocs. And additionally, there are some useful MOS observational strategies which are discussed in the MOS recommended strategies article on JDocs. So to summarize, I have this image of the submission process. So there's a proposal deadline, the one May 1st, okay? And this is where you submit your MOS placeholders. And then the TAC meets and decides which proposals are accepted. And then a long-range plan is constructed, and a fixed orient or a aperture position angle is assigned for MOS spectroscopy and for the target acquisition. And then after you have received your angle, you need to update your program, and you have some time to do this. And eventually, the observation window starts. Okay. JDocs also provides a general guide to preparing NIRSpec MOS observations, and this article includes specific considerations about how to construct the catalogs that you're going to use, which contain the sources that you want to put behind the shutters, NIRCam pre-imaging, and some other things. I'm only going to talk about the first two. Okay. So NIRSpec observations planned with the MPT require planning catalogs. And catalogs produced from HST, ACS, or WIF C3 imaging have sufficient relative accuracy for detailed MOS observation planning and program updates. In other words, if you already have images of your field with these two instruments, or either one of these instruments on HST, that's enough to plan your your MOS observations. Okay, if not, you probably should request NIRCam pre-imaging. Okay, the catalog should be as complete as possible, including not only sources of scientific interest, but all other sources in the field to be able to identify potential contaminants. The relative astrometric accuracy of the catalog is important for target acquisition to put science sources in the tiny shutters. For example, a relative astrometric accuracy of 5 milliarc seconds in the catalog is necessary to deliver NIRSpec MSA target acquisition accuracy of 20 milliarc seconds. Catalog accuracies of between 5 and 10 milliarc seconds are required for meaningful use of the centering constraint in MPT, which can help to limit slit loss and wavelength calibration uncertainties. There is a way to select the shutters to produce a long slit, right? For those, you don't need a catalog because APT has some template for this. Okay, about NIRCam pre-imaging. So NIRCam pre-imaging may be needed for MOS observations where imaging and catalogs are either non-existent or insufficient astrometric accuracy to plan detailed MOS observations. Right. Also make sure that your image has sufficient signal to noise in the sources that you want to observe. If not, you should request NIRCam pre-imaging. A few words about the ETC and NIRSpec MOS. So you're going to use to determine the required exposure and detector readout parameters for your NIRSpec MOS observations, including the target acquisitions. You're going to use your exposure time calculator, which Omaira described yesterday. And of course, you're not going to run a calculation for every single source that you want to observe, all 100 sources that you want to observe. Okay, so what you do is that you perform these calculations on the ETC by bracketing the range of expected source brightnesses in your field in the wavelength bands of interest, avoid saturation of the brightest sources. And this has to do with a question that Roberto asked yesterday, right? Yes. So this is the same thing, okay? All right. Now, I want to tell you about an ancillary tool that was not covered yesterday. It's called the NIRSpec Observation Visualization Tool, NOVT. This is a Python application that provides a simultaneous views of both NIRSpec and NIRCam fields of view of a given sky position for assistance in planning NIRCam pre-imaging for NIRSpec. It is not required for planning, but is very useful. And so you can determine from viewing in Aladdin or from using this tool whether an aperture position angle special requirement is needed. So I told you that it's the space telescope that's going to assign you an aperture position angle. But if your source is not symmetric, right, then you're gonna need to tell them, look, I really need to be in this range of position angles. And so you will do that as a special requirement on APT. Okay. Yeah, some use cases may need such a constraint, but for scheduling flexibility, a minimum range of approximately 20 degrees to 30 degrees is recommended, the range for the aperture position angle. Now, it's not guaranteed that they're gonna give you this, okay? All right, so about this tool, if you go to JDocs and look up this acronym, you will find instructions on how to install it and how it is used. Okay, so let me look at the time because next I'm going to show you a video which is a bit long that will show you an example of how you load a catalog on APT and how you do your plans for the first step of the submission, okay? So this is the part where if you're not interested in this mode, read your email or whatever. And the reason why I'm showing the video, not doing it myself, is because there's no way I could have done a better job than they have done. Okay, so I'm gonna get out of here and try to find the video. Okay. All right. So hopefully the sound will work. So this is a video on MSA planning, the MSA planning tool in APT, okay? It's already available in the APT versions which you have. And here we go.
Okay, so first, I have a few slides to basically describe what the planning tool is going to do for you and how it works. So again, there's a fixed grid of shutters and micro shutters in the MSA, and they are separated by small bars. And if the source lands behind a bar, you're not going to see it. So one of the things the tool does is it makes sure that the sources are falling into the shutters before it selects those sources for observation. There is, like I said before, a gap between the two NIRSpec detectors, and so that will possibly require dithering if you need to pick up the wavelengths that are lost in any given exposure. If you want to observe them in a second exposure, you would have to dither a little bit in order to recover those wavelengths that were missing. Again, the MSA has failed shutters like any other device that we make. The failed shutters may be failed for different reasons. There are also shorts between the rows and the columns that have to be avoided during planning, and the MSA planning tool will take care of that for you.
So I don't know if you got that, but all these black things here are failed shutters. They are shutters that fail to open, and so they have planned. The MPT tool knows about this, so you don't have to worry about this. Okay? Yes.
They're not gonna work. Period.
They're not gonna work. Period. Okay. Okay. Excuse me. They're like bad pixels, yes. And when it's in space, there may be, a different combination, and they will have to deal with that. Okay, it's new technology, and and that's what it is. But you can still observe hundreds of objects simultaneously with this. Okay. Okay.
The source positions also require knowledge of the optical distortions in the telescope and in the instrument, and velocity aberrations that are caused by the movement of the telescope with respect to the pointing that it's looking at. So we take all of that into account. We map the positions of the sources to the microshutter array, and then open appropriate shutters there to create those MSA configurations. And I will just say that this is not an easy task. It's easy for one pointing position, but it's not easy when you're trying to track sources through a number of pointing positions, through a set of dithers. That's the hard part. Failed closed shutters look like these, what are sprinkled all over the MSA, these black little dots all over the MSA. And sources, we don't select sources that fall on them. The shorts look like these columns and rows, a sort of a plaid effect there. We try to avoid those as well. The failed open shutters are the ones that will really get you, because there are about 20 of them, I think 19 in the visible area of the MSA. And these are potentially going to cause contamination of your target spectra. So we mask areas of the MSA that are affected by anything that would be caused by a source in one of these open shutters. We mask out those areas on the MSA and plan around them so that you don't have contamination. There's also a button in the planner of the MSA planning tool where you can just elect to instead use these open shutters if you'd like to. They're just poorly calibrated. So again, at each test pointing, this tool will create a series of test pointings in a grid on the sky. You'll specify the spacing of the grid and the extent of the grid, and that at each pointing, the tool will try to plan around the failed shutters, pick up as many sources as it can through all of the dither points. And so it's optimizing the use of the MSA as much as possible, but while also observing as many sources throughout the dithers as possible. Okay, so what you'll need to run the MSA planning tool is an internet connection, and that allows you to get the most up-to-date MSA shutter operability information and to check for guide stars, suitable guide stars in the pointings that you're planning. Also, you'll need that input astrometric catalog. And again, the source positions have to be accurate to less than 15 milliarc seconds in order for the optimal use of the MSA target acquisition. The source catalog must also be complete. And I say this because we don't do any contaminant avoidance during planning. So it's left to the user to check that other sources are not contaminating their slits. And so I'll show an example of that at the end of the demo, or near the end of the demo. Okay, and the products that NPT produces are plans, what are called plans, and those plans are turned into, you'll select the plan and turn it into an actual observation, and it will populate the observation template. Along with that, with these particular pointings, of course, you have particular MSA configurations, and then the set of sources that are observed through that set of dithers is called a target set. So that all that information is tracked by the MSA planning. So next I want to talk about the source catalog requirements. So the first step is to create this catalog of sources. This catalog should be complete. It should contain all known sources in the field. And the reason for that is that you want to be able to check whether the planned sources that you're creating spectra for are impacted by the unintended nearby sources that happen to fall in the same slit. You want to be able to check that the tool itself does not plan around contaminants. So you have to double check that in your plans. The catalog is just an ASCII file. It has to contain J2000 RA and DEC minimally. It should also have target IDs, source IDs, and the observed targets will, of course, be derived from this listing of candidate targets. The header in the file is optional, but it helps to instruct the MPT during the ingest of the catalog. It helps to instruct MPT what the catalog, the columns contain, what type of data the catalog columns contain. Okay, and so because of the small size of the shutters, again, you want between 5 and 40 milliarc seconds are the usable accuracies, and that will depend, whether it's usable or not will depend upon the science that you want to do. So for moderately extended sources, you might be able to get away with 40 milliarc seconds in the relative astrometric accuracy. But less than 15 milliarc seconds is for optimal TA planning and observation with the MOS mode. So next I'm going to show you an APT demo on how to ingest an MSA catalog into APT. Okay, I have APT already started, APT 2020.1 already started. I'm going to start by showing you how to load a catalog. But before that, let me just say that I got this menu here by selecting new JWST proposal. And then what you see is this menu here, okay? So the first thing you'll want to do, well, is, of course, fill out your proposal information. I'm not going to bother with that because it's of no consequence for the demo. I'm going to go to target, and you have a series of selections of different types of targets you can enter. For the MTT, you'll want to define an MSA source catalog type target. So when I press that, there's a pop-up window. I'm going to browse to my catalog. And I know the name of the catalog is the HUDS. No, I'm showing you good spell. Hold on. Good. Let's see. Okay, so it self-populates the catalog name. We'll let that go. And I'll put white space separated is the format that this particular catalog has. So you can see that it automatically tries to identify your columns for you. These set of values here were entered with the catalog. It's an ASCII catalog, and it had a header line that said what each of the columns was. And so the tool was successful in being able to identify that this is the ID, the source ID column. RA and Dec are here. That's a magnitude. And so it can understand certain columns. One that it didn't pick up was the redshift because it's named in a funny way. So I'm going to tell it that it's a redshift. And we're going to use that redshift. So everything else is defined. I'm going to say import. And it shows you the progress. And immediately it tells you there's a red X, there's a problem. Okay, let's look at the first red X. This here, it doesn't like underscores. So what I'm going to do is get rid of this whole thing and just put that as my catalog name. You can rename it to whatever you want to do. Okay, so now it's happy with that. I'm going to highlight the catalog, and it wants more information. It wants the level of accuracy, relative astrometric accuracy. I'm going to put 10 milliarc seconds because it was generated from ATS data, I believe. And then I'm going to say, this is a field that's already observed by good. So I'm going to say that the data are already obtained. The pre-image availability is already obtained. And this is just a way of linking. It tells APT that there's an existing image from which the catalog was derived, and helps to link that information together in the archive. So now I have this entire catalog. It's huge. And so, actually, I don't even know how many sources it is. It should say, I don't see it here. But I'm going to derive a subset of that and use that for planning in the MSA planning tool. So I'll say new candidate set. And I'll give the new candidate set a name first. I'm going to choose redshifts greater than 5 as my primaries. So I click add filter, then new redshift filter. My minimum redshift is 5. I click OK, make candidate set. And now I have a new entry here. It is a daughter of the catalog. And if I click on it, the data from that subcatalog or that candidate set is shown. It tells me that I have 542 sources in this sub-catalog or the candidate set. Okay, those are the items those are the ones that are with redshift greater than 5. Now I'm going to create another candidate set because the MSA planning tool works with two different candidate sets, a primary candidate set with your high priority sources and a filler candidate set. So I'm going to now define a filler candidate set as click new candidate set again, and this time it's just
so I just want to make sure you got this. So you load your catalog, which includes all of the sources in your field, and then you're gonna need to extract from that catalog 2 candidate sets because the tool is gonna need them. One is gonna be called the primary with the main sources that you want to observe, and then there's gonna be a second one. Yep. So this tool looks a little bit, has some of the features of TopCat. I don't know if you're familiar with that, but it will extract from a large ASCII file what you need. Okay.
To be redshift, everything with redshift greater than 3. So now this candidate set is going to actually include the sources from the primary candidate set. Do it the same way. I select the redshift filter, redshift, Has to be greater than 3. Okay, make candidate set. Okay, so now I have 2 candidate sets and I'm all set to go. In this section of video, I'd like to introduce the MPT Planner. The MPT Planner is really the guts of the MSA planning tool. In the MSA planning tool, there are the screen like this. There are 2 tabs. The first one is the planner. The second one is plans. The planner is really the engine for generating your MOS observing strategies or observing programs. It allows you to select several different parameters, and you just go through in sequence and make selections in the planner to define your observing plan. The first thing that you'll have to do is choose the primary candidate list. Here I'm showing the catalog that I generated the candidate list from and the 2 candidate lists, redshifts greater than 3, redshifts greater than 5. I've selected the primary candidate list in this shot, and now I have to select an aperture position angle to test with. So I selected one that I know is a feasible angle for this catalog. Next, I choose the slit setup parameters. The first parameter that we have to decide is what is the default length of the...
Oh, what did I do? Okay. Algo que se me olvidó definir es lo que es un slitless. Un slitlet, perdón. Un slitlet es una combinación de microshutters. Entonces, por ejemplo, estos 3 son los microshutters, las 3 puertitas constituyen un slitlet. ¿Ok?
Y el otro también es algo, el cuadrito grande es un slit grande o...
This represents the entire open shutter area. Okay, it will just let it continue, and you will understand. It has to do with centering and the PSF at different wavelengths and things like that. Yep.
¿Pueden hablar en el micrófono?
Ajá, me preguntan que qué tan grande puede ser el arreglo o el slitless. Entonces, bueno, tienen las opciones
Ya estoy muy cansada, disculpe.
Ok, va a depender de en dónde está tu fuente, si hay un closed, un failed open o failed closed shutter, pero lo más grande pues es el modo long slit. Entonces no lo voy a cubrir, no voy a hablar de él, pero pues lo puedes mirar en JDocs, ¿sí? Ok.
Nada más una pregunta.
Sí,
A ver, no, espera.
con micrófono.
Sí, sí.
No hay nadie oyendo, ¿sí?
Sí,
Ok. Está bien. A ver, algo que no entiendo bien. Los slits son chiquititos. El nodding se va a hacer a lo largo de cada slit o va a generar esa área
Ahorita lo van
abriendo los shutters de los lados. Es lo que no me queda claro.
Ahorita lo van a explicar.
Okay.
¿Sí? Van a explicar
perdón.
la diferencia entre nodding, que es para sustraer el background, y dithering, que es para cosas para mejorar la calidad o cubrir gaps.
Ok.
¿Sí?
Gracias.
Slitlet to use for each of the sources in the field of view. In the case of point sources, we nominally recommend the 3-shutter slitlet. That allows the target to be in 1 shutter at a given time, and then 2 shutters are used for background estimation. Secondly, there is a source centering constraint. A menu from the pull-down lists 1, 2, 3, 4, 5 different values of a margin that can be applied as the source centering constraint, which keeps the sources inside the margin. So let's talk for a moment about what the margin is going to do. What you're seeing here is an image of 5 different images of a monochromatic PSF generated at each of the wavelengths shown under the image. And it's cut off by the shutter, the shutter dimensions. In this sequence of images, the source is actually placed off center. So you can see what a typical MSA source PS point spread function would look like. So you can see that the slit throughput is going to be a function of not only the wavelength and the width of the point spread function, but also of the relative placement of the source in the shutter. So the margin, the source centering constraint margin that we're talking about in the planner, allows you to select sources that are more and more confined to constrained to be closer to the center as you go down this, this table here. Also, we've shown the minimum relative flux transmission at roughly 3 microns, just to give you a comparison in physical units of what the effects are on the throughput, on the slit throughput at that wavelength. And you can see that it ranges from 12% with almost no margin to 85% as the minimum relative flux transmission. So this is relative to the source centered in the shutter. So as you can see, a tighter constraint results in a higher flux for the source, but it may also result in fewer targets that are observed. So next I want to talk about the benefits of dithering. In addition to improving the sampling of the PSF and correcting for hot or bad pixels, dithering also helps you to improve background subtraction. Recall that I said in a 3-shutter slitlet there would be 2 shutters for background estimation, 1 for the target spectrum. And so you can see in 3 different exposures, we've tilted the telescope, we've nodded the telescope a little bit. This is called nodding. It is a parameter in the MPT planner which you can enable or turn off. And the result is that for a 3-shutter slit, you'd get 3 exposures with the target in each of the different shutters of the slit. Additionally, you can recover, for example, lost wavelengths that maybe fall in the detector gap by using a fixed dither. This is a second option. The 2 options can actually be used together. You can do both nodding and dithering. The dither allows you to move the sources to a different part of the detector, the source spectrum. And so you get additional exposures with nodding if you have elected to use that at a different dither point on the MSA. And to do this, you are the fixed dither requires a reconfiguration of the microshutter assembly. So that will be an overhead that you will have to pay for that large dither. You can, in doing so, you can observe additional sources behind the bars or that were behind the mounting plate in the earlier set of nodded exposures. It also helps to mitigate the effects of light leakage through the MSA because each of the shutters in the MSA have a finite contrast and they're all different from one another. They're all roughly 10,000 or better, but there are small light leaks that can occur, and one of the ways to mitigate this is by moving the sources to a different detector location or perhaps even a different location with respect to the shutter itself. The edges of the doors have small light leaks that can happen even on a shutter, on a smaller than a shutter basis. So MPT is the tool that will actually take all of the dithers into account and will attempt to observe as many sources as possible through that set of dithers. So that's actually the hard part, is tracking the sources through the set of dithers. But MPT does that for you. So how does this actually work? What happens is MPT starts by creating a grid of test pointings over the area of the primary candidate list. And it uses the user-specified search grid parameters. So both the extent, the height and width, and the cell size of the search grid are specified in the planner. Then the sources are mapped to the MSA plane. I'm just talking about the primary candidate list at this time. At each pointing, MPT then checks each source in the primary candidate list, and it does so in the order that they're listed, which turns out to be important. And unless you also select to do shuffling, which we'll talk about later. So what MPT tries to do is it tries to place the sources one at a time into the MSA configuration. It checks them at all dither points. It checks their background shutters at all dither points, and it makes sure that the shutters that are all operable, that need to be operable, and it makes sure that there are no conflicts with other selected sources. So therefore, that's where the ordering of the sources in the candidate list matters, because if you place a source down on the MSA, it prevents other sources nearby from also being selected for the same exposure. So there is a sequence to this. So it generates what we call a heat map. This is a grid of all the results of testing those viable sources, how many sources it can put into the MSA configuration at each of the test pointings from the search grid that you've defined. So the weights of all of the primary sources, if weights are used in the planner, the weights of those sources are summed at that grid point and then are inserted into an internal heat map and kept track of. So eventually, you can see where I'm going with this. These brighter areas of the heat map are preferentially the ones to select, that MPT will select for you as the best pointing to obtain the most sources, and certainly those of the highest weight if weights are used. This is just showing a zoom in of a small area of the heat map. On a very small scale, you can see that there is still structure, even at the shutter scale, within the shutter scale. So when you're doing your MPT testing and it's certainly fine to do a coarse grid sampling on your heat map or on your search grid to begin with, and then but when you're finalizing your plans, it actually may pay to do a fine sampling of the heat grid to see basically if there are improvements in the number of sources that you can obtain. So MPT then selects the best pointing from this heat map, and it will do this selection for the entire set of dithers. And then these results are solely based on the primary candidate list, as I mentioned. The primary candidate list is the one that drives the pointing selection for your plans. If fillers are added, that is a secondary step. So I just wanted to point that out. So the MSA configurations for each of the major dithers then in the plan are built, and then the filler sources are added in after the fact. A plan is then generated in MPT. Plans have pointings and sources that will be observed at each of those pointings, which we call a target set, and associated MSA configurations that MPT generates for those pointings. Then the user will select one or more of these plans to generate a MOS observation from.
So it's easy to get lost.
Now I'm going to demonstrate the planner.
I've watched this video so many times. So I just want to summarize what just happened when they were describing the heat map. So what the planner is doing is that it's trying different pointings, diferentes apuntados, ¿ok? Da su catálogo y va a optimizar y tratar de encontrar el apuntado que les permite ver el mayor número de fuentes en su primary catalog, ¿sí? Y luego va a utilizar ese apuntado junto con la configuración que ustedes escogieron, es decir, qué dispersor quieren. El dispersor les dice qué longitud de onda van a cubrir y qué resolución espectral. El conjunto del el apuntado que escogió la herramienta de optimización más todos los parámetros de la configuración de cómo van a observar. Eso también incluye, por cierto, un filtro. Entonces, cogen un dispersor y para que la traza espectral no esté muy larga y se solapen los shutters, le ponen un filtro para que el rango espectral no sea muy grande, ¿okay? Entonces, la configuración consiste en el dispersor, el filtro, los D-rings, el nodding. Eso más el apuntado constituye un plan, ¿ok? Muy bien. A ver, ahora sí lo...
Aida. Aida.
The use of the planner and,
sí, ¿hay una pregunta? Sí.
Entonces ya se tiene un mapa de píxeles calientes, ¿no? Predeterminado. ¿O eso se va a saber cuando ya se observa?
No, esto es antes de que te asignen tu ángulo en el que va a estar orientado NIRSpec. Entonces, el mapa, el heat map, lo que es que te dice cuál es el apuntado en el que puedes observar más fuentes. ¿Ok? La herramienta va a tratar diferentes apuntados, ¿ok? Y va a ver cuántas fuentes caben, dado ese apuntado en los shutters que funcionan, ¿ok? En tu catálogo, las fuentes que tú pusiste pueden tener pesos, les puedes poner pesos más grandes a las fuentes que más te interesan, ¿ok? Y luego, la herramienta de optimización, tomando en cuenta toda esa información, los pesos y los apuntados, etcétera, crea este heat map eso es lo que entiendo hasta ahorita, ¿ok? Okay.
Entonces, ¿cuál es la diferencia entre nodding y tethering? No me queda claro, los confundo mucho.
Ok, nodding es esencialmente hacer dithering, ¿ok? Es un modo de dithering, ¿ok? Nada más que el nodding está, el objetivo del nodding es la sustracción del background, ¿ok? Entonces, las configuraciones que ya están en APT para nodding son para mejorar la sustracción del background. Entonces, en un momento dado tenían, escogieron un Slitless configuration, que eran 3 shutters, ¿sí? Ponían la estrellita, por ejemplo, en el shutter del medio y obviamente los otros 2 pues eran para sustraer el background, ¿ok? Si quieren mejorar la sustracción del background, entonces escogen nodding, ajá, y entonces eso simplemente mueve a la estrellita del shutter de en medio, al de abajo o al de arriba, y entonces la herramienta, y entonces el pipeline va a usar esa información para mejorar el background subtraction. Ese es el nodding, ¿ok? Y luego el dithering, la diferencia, el nodding es una especie de dithering, ¿ok? Pero el dithering, hay otra opción en APT que se llama dithering y cuyo objetivo es hacer cosas como mejorar el sampleado del PSF, del Point Spread Function, cubrir gaps, ¿cómo se dice? ¿Cómo se dice? Se me fue la palabra. Bueno, ven que hay failed shutters, entonces si se interponen, pues lidiar con eso, lidiar es la palabra, lidiar con eso. Entonces el dithering les permite hacer todas esas, cubrir gaps, lidiar con failed shutters, mejorar el PSF, ¿sí? Sí.
Ok.
Hay otra pregunta,
Gracias.
perdón, micrófono, sí.
Hola, sí, no es pregunta, es creo que un complemento, a lo mejor le ayudan a Luisa.
¿Sí?
No sé si haya sido un caso especial, pero ahí en el video lo que se ve es que el nodding es a lo largo del slit,
¿Sí?
Y el dithering es a través del slit.
Sí,
Entonces, no sé
perfecto.
si eso sea siempre, pero eso es lo que se vio allí.
Sí, en general, el dithering te va a mover tu fuente, no la va a poner en la misma parte del detector. Entonces, por ejemplo, si antes estaba en un gap, pues ahora ya no va a estar en un gap. O si estaba en un failed shutter, pues ya no va a estar en un failed shutter. Sí, sí la mueve en el detector. Ok, gracias. Entonces, pues continuamos.
The generation of plans and how to evaluate those plans.
Perdón,
in the plans
hay otra
pane.
pregunta. Sí, perdón.
Más que una pregunta, es como un comentario. En mi experiencia con MOS, no aquí, pero en otros MOS, el asunto de obtener el máximo número de objetos para observar queda peleado con obtener el máximo en longitud de onda que quieres, en intervalo de longitudes de onda que quieres. Si quieres poner muchísimos objetos, tienes que restringir tu intervalo de longitudes de onda porque si no se van a empezar a traslapar y te va a causar problemas, ¿no? Y entonces ahí es una cuestión de qué es lo que uno realmente quiere. Si obtener un intervalo de longitudes de onda extenso para tener la mayor información en ese sentido, eso te reduce el número de objetos que vas a poder observar. Si
Ajá,
quieres,
este modo, después voy a discutir Wide Field Slitless Spectroscopy, que es lo que tú estás describiendo. Pero gracias a que hay puertitas, es como si tuvieras un montón de rendijas. Entonces solo dejas pasar la luz de tu fuente, pero además, como dije, le pones un filtro, no solamente tienes el dispersor, sino que pones un filtro para que tu traza espectral no sea muy grande. Entonces no va a haber trazas espectrales demasiado grandes en este caso.
Pues
¿Okay?
sí, es justo
pero,
lo que estoy diciendo. Si quieres una
exacto.
traza espectral grande para tener información de muchas longitudes de onda, vas a tener que reducir el número de objetos.
Ajá, entonces pones un stop filter para que no sea tan grande y mitigar ese problema. ¿Sí? Ok, muy bien. Entonces, seguimos.
Of the MSA planning tool. Now we want to use the MSA planning tool. We want to go directly to the MSA planning tool. We don't go to the observations. That's going to be done afterwards. So let's go to the MSA planning tool. It's up here in the toolbar. Okay. First thing you'll notice is that there are two tabs in this MSA planning tool. The first one is MSA Planner, and the second one is this plans area where you will evaluate the plans that you've made against one another. Okay, so I've already it remembered it remembered the values, but you would just select from these pull-down menus whatever candidate sets you've defined. Now, in this particular case, I showed you how to read in the Good Spouse, but I'm going to actually be working with the HUDF catalog that I preloaded. It was already baked in the cake there. So let's work with the HUDF. I'm going to select my primary candidate set, which is the redshift greater than 5 sources, and I'm going to select my redshift greater than 2 sources as the filler candidate set. Both lists have to come from the same catalog. You cannot plan an observation, a Moss observation, from 2 separate catalogs. I want to make that clear. The first thing that normally you would see here is 0. And so I'm going to let it try to select 0 to show you what will happen. So this little twirly thing here is telling you that it's trying to get a guide dog, look for guide stars that are suitable guide stars in that area, based on the catalog that you gave it, the candidate set that you gave it. So it gets a red X because that is not a successful or a feasible angle. And the feasibility, the general target visibility tool will give you the feasibility of different angles for your source. For this particular field, I know, for this particular pointing, I know that 135 works well. I'm just going to use that, and it should get rid of the red X. Yeah, okay. So now we define the split setup. The split shapes that you have available to you as default split shapes are these 4 selections, 1, 2, 3, and 5 shutters. If sources are point-like, we normally recommend 3 shutter slitlets for those types of sources. So I'm going to use that because these are distant galaxies. They're probably going to be most likely point-like. Now you have the option to constrain the centering of your sources. As the sources get further and further towards the edge, it affects the flux calibration, of course. You have more significant slit losses. I will show you a slide on that when we get back to the slides. So I'm going to select the midpoint for this, just to demonstrate this. I did in that. That's left midpoint. Yeah, anyway, we'll leave it at midpoint. I am going to select the dithers next. The pointing setup is the next section. I want to nod in the slitlet, which means that I'm going to get 3 different exposures where the targets are going to be placed in the first exposure in the center of the slitlet, but then in the next exposure, targets will be at the top, and then in the final exposure, targets will be at the bottom. And the reason for this is dithering helps with all of the pixel-based artifacts that are on the detectors. So this nodding, it basically is coming for free. It's a very slight movement of the telescope. You don't have to reconfigure the MSA in order to get this. So no overhead from the MSA reconfiguration for this. I'm going to define that I also want to dither by more than just nodding. I want to actually reconfigure the MSA in a few other places. And that helps to, for example, across the gap between the 2 detectors, as I mentioned before. That's one of the reasons why you might want to dither. Another is place those sources into different areas on the detector to wash out over any quantum efficiency differences between different areas of the detector. Okay, so I have specified already these 2 different dithers. So what you know, let me just get rid of this so you can see. This is what when you select fixed dithers, the table comes up like this. It grays out the fact that you've already got 1 dither point. That's the central dither point. So you're basically already getting 1. So you add any more. So this will be, I added a second one, and I'm going to give it a dither of 15 shutters, just to demonstrate how this works. So I'm going to have 2 MSA configurations, and it tells me that right here below, below the table here. Okay, so I'm happy with that. I'm not going to discuss this right now. It is a little bit complicated to talk about right now. I will try to go back and remember to talk about that. I'm going to select the prism. I have choices here. I have a lot of choices between gratings and filters, but I'm just going to show you an example of using the prism. The prism has shorter spectra, and so I should be able to get more sources onto the MSA without contamination. It automatically populated my search grid with a center and a width. and a height. And those are based on the size of the candidate set for the primaries, I think, or on the catalog. I'm actually going to limit the selection a little bit. These are editable parameters. I'm going to make it 200 by 200 for my search grid. And I am going to keep the step size of 5. I think when you first start from scratch, it says 30 arc seconds, but I'm going to use a smaller separation. There's about 1,681 pointings. If I change this to a different number, like 3, and then click out of it, you'll see that it figures out how many pointings you have. So I'm going to use, like I said, 5. Okay. And this, I'm going to click off these parameters here. I'm not going to use target weights right now. I want to show you the difference between using them and not using them. So I'm going to do my first plan with not using them. Again, because I have 2 dither points, 2 fixed dithers, I need 2 configurations minimally in order to derive 1 target set. Now, the reason we give you a chance to enter more, and it has to be, in this case, it tells me multiples of 2 in order to get a complete target set, because I need to complete the plan for those 2 dithers each time. So the reason we give you the option to add more, like 4, 6, 8, is because then you'll get more target sets. You'll be able to observe more of your primary targets from the list of primary targets that you've gotten, that you've specified. I'm just going to put 2 just to show you how it works. It will tell you if it used this name in a plan that you've already developed, it will tell you, no, you can't use the same name. So it forces you to rename this. So I'm going to call it 2 dithers and plan A. You have to click out in order to activate the generate plan button. So now I'm going to click generate plan. So it's working on looking at that test grid, that search grid, and it's trying to figure out, for the 2 dithers that I've specified, it's trying to find a good starting point for those 2 dithers, which picks up the maximum number of sources. So it's come up with a conclusion. It popped me right over to the plans pane here. And that's where you do the plan assessment or evaluation. Now you can see I've already played around with this. I've already had 2 plans already. I'm just going to be repeating live to you what these 2 plans show. So, okay, I must have used a different set of parameters in the planner here. I think I used a different dither actually previously. So you see there that there are 6 exposures in this plan. There are 46 primary sources that this plan observed, and 125 secondary sources or fillers that is observed. So this is just a status line for each of the plans that you develop. So it's a quick way to compare the plans. Let's see. You can export the plan itself and share with other members of your team, and this replan button is used to, for instance, if I click this, it goes back to the planner. It remembers the plan parameters I used last, and then I can tweak any of those parameters. So for instance, if you were in the final phase of your planning for your program update, you would switch to the aperture position angle that you were given as your assigned angle. And so replan is a quick way to do that. But I'm going to go back to the plans pane. And so now I've shown you how to do it without weights. Let me just investigate all the other information that you have available to you in this pane. So eventually we're going to select one of our plans that we like the best, and we're going to create an observation from it. That's what that button is for. You can export a plan and import plans here. You can also describe a plan. So I have one. I'm going to highlight the one we just made, and I'm going to click describe plan. Describe plan shows me what all the plan parameters were that I used for that particular plan. It helps you keep track. That out. And then, of course, you can delete any plans that you don't want to maintain there. Okay. So with the plan that I've highlighted here, it has 6 exposures. It has 3 exposures for the 3 node positions in the first configuration. And in the second configuration, it's got the 3 node positions. So it's got a total of 6 exposures. It says configuration 1, exposure 1, node position 1. The next one's node position 2, the next one's node position 3. That's what that nomenclature there means. It tells you what the plan number is. It's from plan 3. So you can keep track of what you're doing. Gives you the RA index of the pointing, and in a different format here, the aperture position angle, the grading of that exposure, and then the target set size. This is the total number of targets from your list that were observed, so both primaries and fillers. And it gives an indication of the total weight based on the weights of the sources that you have picked up from your different candidate lists. If you click, let's see, I'll do this one. So I'm going to just, let me just review what's down on the bottom of the page before I show you some of these buttons. So below, whatever's the...
Ok, entonces, ahorita lo que está haciendo es enseñando diferentes planes. Eventualmente va a escoger uno para crear una observación. Ok, son las 10:30 y es hora de tomar la foto. Vamos a hacerlo en coffee break mejor. ¿En el coffee break? Ah, ok. Entonces, a esto todavía le quedan 20 minutos. Entonces, como quisiera cubrir un poquito Slitless Spectroscopy también, déjenme ver. Simplemente está comparando, lo pueden ver ustedes después. Está comparando diferentes planes. Quiero ir a la parte en donde crea la observación. Sí, adelante. No. Ok. Sí.
Ahí en las opciones de configuración venía Prisma y Clear. No sé si entonces este sistema permite poder observar diferentes rangos de longitudes de onda inclinando ese prisma, o por qué te dan la opción de poner el prisma.
Significa que no utilizas un filtro para restringir el rango espectral que vas a observar.
Sí, eso me queda claro, pero si tú tienes un prisma, evidentemente lo puedes mover poquito y entonces observas un rango u otro. No lo permite.
Creo que no.
Ah, ok.
Ok, voy a verificar, pero creo que no. Es simplemente, ¿quieres un rango espectral más pequeño o todo el rango espectral disponible?
Ok,
¿sí?
gracias.
Ok, entonces, más bien como si quiero cubrir... Ajá, sí, perdón, ¿otra pregunta?
Hola, Aida.
Sí.
Una duda. Supongamos que ya tengo el campo definido, ¿no? O sea, ya todo anclado. Y quiero hacer dithering, pero si el tiempo de exposición son 10 minutos y hago dithering, entonces cuando haga dithering también son 10 minutos, ¿no? Es como si estuviera moviendo el field of view nada más.
Sí, correcto.
Ah, ok. Ok, y todo eso se contempla, ¿no? En el ETC.
Sí, el APT, el ETC te va a decir cuánto tiempo de exposición necesitas para cada apuntado del dithering.
Para cada apuntado.
Ajá.
Ok, entonces
y
voy a hacer
ajá.
el APT.
Ajá. En APT va a calcular todo el tiempo de tu programa, en el tiempo total de todos los ditherings que vas a estar observando, más el overhead, ajá, sí.
Ah, ok, yo pensé que todo eso se hacía con el ETC. Ok, gracias.
Ajá, más bien, como quiero cubrir la parte de Slitless Spectroscopy, la parte que falta es en la que les muestran también cómo usar esta herramienta ancillary tool que se llama NOTV, ¿ok? Entonces, esa parte pues me la voy a saltar, pero la pueden ver ustedes. Hay videos creo que nada más dedicados a NOTV. Y me tengo que acordar un poquito. Voy a dejar que terminen de ver.
¿Esto se muestra también en Aladdin? ¿Cuáles son las que están escogidas?
Sí, entonces, por ejemplo, este es Aladdin, ¿no? Entonces, este es Aladdin y no sé si alcanzan a ver, pero aquí se ven los Slitlet con sus tres pequeñas, bueno, este es el Tree Slitlet, escogieron el Tree Slitlet, la configuración de Tree Slitlet y ahí las ves, ¿no? Y también lo puedes ver usando esta otra herramienta, entonces, eso pues no lo voy a cubrir. Una disculpa, pero es un poquito... De hecho, el entrenamiento sobre esto es de 4 horas y no sabía yo cómo meter 4 horas en 1 hora aquí, pero sé que lo pueden hacer en casa si están... Si tienen preguntas acerca de esto cuando estén de regreso, pueden contactar al Help Desk, es lo mejor. A lo mejor yo puedo contestar algunas de sus preguntas, pero es mejor que tengan la respuesta oficial, ¿sí? Y también hay mucha ayuda en Jwst. Muy bien, entonces...
Este video, sí.
El video está en la presentación que voy a subir. Les dije que rehice mi presentación y todavía no la he subido al repositorio, está la viejita. Entonces voy a poner la nueva y ahí está la dirección del video, ¿sí? De este video largo de 1 hora.
Y también está en el Jwst Observer YouTube channel, ¿no?
Sí, está en el Jwst Observer YouTube channel. Muy bien, entonces, ¿vamos a hacer la foto ahora o después? Después, en el coffee break. Ok, muy bien. Entonces, esta mañana la estamos dedicando, bueno, esta parte de la mañana a espectroscopía multiobjeto y como les dije, o para los que llegaron tarde, hay 3 instrumentos con los que uno puede observar simultáneamente múltiples objetos. Uno es el que acabo de cubrir ahorita y luego está otros 2 que voy a cubrir ahora. Ok, entonces... Ya me perdí. Permítanme tantito. Ay. ¿Dónde está mi mouse? Ok, ahí está.
¿Está en el repositorio o dónde está?
Este sí está en el repositorio. Ajá. Ay. Ok. Sí, pero quiero en realidad. Ok. Entonces, ahora vamos a hablar de Wide Field Slitless Spectroscopy. Y hay 2 instrumentos en Jwst que permiten hacer esto, NIRS y NIRCam. Y este es el focal plane de James Webb, y entonces aquí está NIRCam y aquí está NIRS. Les recuerdo que NIRCam tiene 2 módulos. En el modo estándar se observan simultáneamente con los 2 módulos, pero se puede observar nada más con uno, me parece, ajustando los parámetros en APT. Y les recuerdo que la manera de obtener espectroscopía multiobjeto es usando un GRISM, que es la combinación de un grating y un prism. Ok. Entonces, aquí muestro las longitudes de onda cubiertas por NIRS y NIRCam para este modo de observación. Y las resoluciones, el resolving power y el campo de visión. Entonces, hay estos highlights acerca de el Wide Field Slitless Spectroscopy. So, like I already said, with this mode, you get spectra of all sources in the field of view of the detector. And this is just to give you an idea of what you can do with this. So in case you didn't know, if you point at a blank area in the sky, a blank extragalactic area in the sky, you're going to find that there are, on average, 3,000 faint galaxies with AB magnitudes of less than 28. Okay? So, you can get almost complete coverage from 0.9 to 2.2 microns with NIRS, and from 2.4 to 5 microns with NIRCam. So they have different coverages, okay? The resolving power of these configurations is sufficient to measure individual emission line fluxes and diagnostic line ratios, okay, for these galaxies. And so these observing modes are ideal for detection of high redshift galaxies, for example, via the Lyman alpha emission line for galaxies at redshift greater than 5.6, between 5.6 and 17. So you're going to start hearing about redshifts which are really, really high, but that's what James Webb was in part designed to be able to observe. So you can detect Lyman alpha. We don't know if there will be Lyman alpha at this redshift, but in principle, if it was there, you would be able to detect it. The line, I'm talking about the line. And then Lyman alpha at redshift greater than 18, and optical H alpha emission lines at redshift 2.8 and 6.6. Now, obviously, Lyman alpha is a UV line, so you may wonder, how can you observe it with infrared detector? Well, because it's redshifted into the wavelength range of James Webb, okay, due to its high redshift. Okay, so the spatial resolution allows you to map emission lines on physical scales of a few kiloparsecs across redshifts greater than 2. These observing modes are efficient for blind emission line surveys and detection of continuum breaks in high redshift galaxies. There are no slit losses compared to slit spectroscopy. If you put a slit, you're losing some of the light from your source. Okay, but in this case, you're not blocking the light like with the microshutter array, so you don't have slit losses. And use of cross-dispersed spectra from true grisms allows you to mitigate contamination due to spectral overlap. And I showed this yesterday when I introduced the instrument. So you will get spectral traces in one direction, in the X direction, let's say, and you may have overlap of spectral traces from sources which are nearby. But then you will take, with another grism, you will produce spectral traces in the perpendicular direction, right? And then by looking at both, you can disentangle which spectra is from which source. Okay. So now I'm gonna focus on NIRS wide field slitless spectroscopy. Right. So the field of view is 2.2 arc minutes by 2.2 arc minutes, and I'm going to explain what the pupil wheel is the wheel that contains the filters. So you have these filters available, and this other wheel has the grisms on it, the two perpendicular grisms that produce spectral trace perpendicular to each other. Okay, the resolving power is 150 at 1.4 microns, and the wavelength coverage is 0.8 to 2.2. Okay, so here are the pupil wheel, which contain the filters. And I'm not an expert on this instrument, okay, so I don't know what all of these are, but you can look them up. Maybe they are useful for your science. And then these have, oh, sorry. What did? Okay, sorry. We're going to cover coronagraphy and aperture mask interferometry later, okay? Right now, we only care about the point is that you're going to need, for this, you're going to need to select a filter, and I think it's mandatory to use the two grisms to disentangle the traces. Okay. So here I'm showing the filter throughput curves for the filters which are available with NIRS, wide field slitless spectroscopy. And these filters, of course, limit the wavelength range of your spectral trace that you get with your disperser, with your grating, with your grism, sorry. Okay, I'm not going to go into this. I already explained that you use two grisms to obtain traces in two perpendicular directions. And, well, these just show you spectral orders in different filters. It's very technical information. This is nice. This is a simulated grism image using 3 blocking filters. And so it's very hard to see the blue, but you can see red and green. So you see, if you put a blocking filter in front of your grism, then you will only get the red if it's the right filter, or just the green, right? And so you don't have all of the wavelength range, and so that this helps you with overlapping, mitigating this problem of overlapping traces. Okay. Right, okay, each instrument is different in how you do dithering and what sequence of steps you need to follow. I'm not gonna go into that because I'm sure you're already very tired. I'm just gonna show you but you can do parallels with this mode also. This is just showing a parallel example. I want to go to this image, which I already showed yesterday. So you have your cluster of galaxies as the direct image. And with this particular combination of filter and grism, you get for each source in this image spectrum, right? And well, I'm trying to find the region where you see some overlap of traces. Not okay. Maybe here. This is longer. And then here you get them in the other orientation. Okay? Ah, okay. Yeah, sure. I think it's in your pocket guide. I'm not sure, but. Right, so this is continuum and this is line sensitivity. Okay? Mm-hmm. Okay, and this is just a science simulation that shows you that with these you can detect a break, okay, a Lyman break, if you're interested in this science goal, using this technique, okay? Okay, and then there is this other instrument, NIRCam, that also offers wide field slitless spectroscopy capabilities. So it has a slightly different wavelength range, longer wavelength range. It has the same field of view per detector. What else? Okay, it has a different set of filters, obviously, because you have a different wavelength range. It has higher resolving power in this wavelength range. And it also has 2 grisms. Right, and there's a wheel that you need to rotate to put the right optical thing in your path, depending on what you want. This is the transmission curves. So this is the total of the instrument and JWST. And this is for the long wavelength channel of NIRCam. And again, it's the same technique of dispersing in 2 perpendicular directions to separate your traces. Okay, sorry. Here are the sensitivities for NIRCam, wide field slitless sensitivity, continuum, and line. Again. And okay, this is the science target simulation. So the different region of the sky than I showed you before. And this is what you get, I think, after background subtraction. There's another image that shows you without background subtraction and with, I think this is it, yeah. Okay, so here are grism C and grism R, which are perpendicular to each other. And for these 3 different filters, it shows you without background subtraction what you would obtain. It's simulated, okay? And then once you do the background subtraction, you see that you can see, especially in this filter, better your spectral traces. And this is just a list of useful resources on wide field slitless spectroscopy for each one of the instruments. And you can also look at the James Webb GTO programs that use this mode and the ERS programs. This slide is going to be in the repository after. I'm going to try to upload it before coffee break. Okay, so this concludes my presentation on multi-object spectroscopy. And I don't know if you have questions. And like I said at the beginning this morning, if you go to the strategies pages or the roadmaps, I can't remember which one of these 2, you are going to have a dedicated article on which one is best to use, the MSA, the microshutter assembly, or the wide field slitless spectroscopy. Okay, and the differences are, again, the field of view, the wavelength range, and the resolving power. Okay. All right. So we can maybe do the Yeah, questions? Yes.
Para esta se usan los detectores que están, digamos, abajo, ¿no?
Sí.
¿Los otros quedan ocultos o se pueden usar para imagen directa al mismo tiempo?
Perdón. Si,
O sea,
si no pones el GRISM, vas a obtener una imagen directa. Si pones el GRISM, entonces se dispersan las fuentes.
Exacto, pero se dispersan los dos de abajo. Son 4 detectores de cada lado, ¿no? ¿O son 4 detectores en total?
Para NIRCam.
Sí.
Ajá.
2 de ellos están ocultos cuando pones el grisma, o sea, no les llega luz,
Ajá.
o se pueden usar para imagen directa al mismo tiempo.
No me acuerdo, lo puedo checar. Sí. Tú eres el óptico, pero voy a checar, ¿sí? No me acuerdo. Demasiadas cosas.
Yo creo que... Sí, yo creo que no, yo creo que es una cosa u otra, ¿no? Que estás cambiando la rueda, ¿no?
Ok. Sí, pero lo que él decía es que como hay varios detectores, a lo mejor puedes hacer algo en una y otra cosa en la otra. Pero no sé si todo pasa por la rueda y entonces eso es lo que no sé, no me acuerdo. Ajá. ¿Alguna otra pregunta?
Aida, una duda.
Sí.
Supongamos que quieres observar no en esto, ¿no? Sino con NIRSpec, ¿no? O
sí,
lo que sea. Entonces no tienes la imagen del Hubble, porque ya ves que yo había visto que también si no tenías con NIRCam, si tenías una imagen del Hubble, podías tener la fotometría, para tener las precisiones en las coordenadas, ¿no?
Correcto.
Entonces, el tiempo de NIRCam también se va a considerar, ¿verdad? O sea, si no tienes el campo del Hubble y tú quieres meter la propuesta, pero no tienes imagen del Hubble, todo eso se tiene que considerar, ¿no? Para el tiempo que estás pidiendo.
Correcto, entonces pues vas a necesitar tiempo para hacer tu pre-imaging con NIRCam, más tiempo para hacer la multi-object spectroscopy.
Y si ya tengo la imagen del Hubble del campo, entonces ya no tengo que perder tiempo con NIRCam.
Bueno, tienes que checar primero si esa imagen en principio es suficientemente buena, si es de ACS o WIFC3. Ajá. Pero tienes que checar que sí cubre una buena porción de lo que quieres observar, porque como viste, el simulador va a apuntar en diferentes direcciones, con diferentes ángulos, y solamente van a entrar las fuentes que entran, ¿no? Para ese apuntado. Entonces, sí.
Ok, gracias.
Y también tienes que checar que tu imagen tiene suficiente señal a ruido para las fuentes que te interesan, etcétera, ¿no? Que es suficientemente grande para cubrir a un contaminante que potencialmente entre en tu field of view, ese tipo de cosas. Sí. Hay una lista de cosas que checar sobre tu imagen HST en JDocs.
Sí.
¿Alguna otra pregunta sobre espectroscopía multiobjeto? Muy bien, tienen muchas opciones en qué pensar. Muy bien.
Y toda la información está en JDocs.
Ok.
¿Quieres que ponga yo mi computadora para que tú hagas lo de tus presentaciones?
¿Qué presentación? ¿Que la suba?
Yo puedo
no, me da tiempo. Bueno, como quieras. Hay otra pregunta, sí.
Gracias. Yo no he oído aquí nada, pero yo supongo que los pipeline y la reducción de datos va marchando también junto con todo, ¿o nos vamos a tener que pelear con eso en el primer año?
Estoy segura que van a haber problemas con el pipeline, pero va a haber un pipeline. Va a haber un pipeline que va a tratar de entregarnos productos que están relativamente listos para hacer ciencia, porque es bastante complicado todo el proceso del pipeline, ¿no? Entonces, lo que haces es yo creo que va a ser similar a HST. Cuando bajas tus datos, pasa por el pipeline, justo cuando estás bajando los datos, y ya te los entrega, pero siempre han habido problemas. Yo me acuerdo cuando instalaron el nuevo espectrógrafo COS en HST, tenían un pipeline y algunas herramientas, y algunas cosas funcionaban y otras no, y las fueron mejorando conforme avanzaba el tiempo, sí. Pero además, como saben, las cosas van a cambiar una vez que esté probado el telescopio ahí, y pues van a ajustar, me imagino.
Las recomendaciones de
Es que
la
reducir
gente
MOS
de
es
James Webb.
bastante complicado.
Decía que las recomendaciones de la gente de James Webb es que construyamos todos en Python.
No, la otra cosa
Esa es
es
la
que-
recomendación para que al final todos tengamos las herramientas disponibles para todos los modos de observación.
Sí, iba a agregar también que para los datos de James Webb que ya están archivados, pues van a haber diferentes versiones del pipeline. Siempre escojan la última versión del pipeline, si tienen la opción de escoger. Sí.
Y algunas Early Science han puesto como objetivo, como cosa contributiva, que van a producir pipelines y subproductos, ¿no? Entonces vamos a poder utilizar las herramientas que usen ellos.
Y ahora sí que están dando como impulso o valor a las propuestas que van a hacer todas las herramientas públicas. Entonces eso también tiene beneficio para la comunidad en general.
Te dejo todo. Sí.
Sí.
¿Quieres el micrófono?
Va a ser afuera en las escaleras. Ahorita es el coffee break. Uy, sí, está bien, muy bien. Yo no revisé la agenda. Es hora del coffee break, pero antes de que agarren su café, por favor. Vamos a tomarnos la foto del evento a las escaleras de la entrada del instituto. Sí, ya nos deben de estar esperando la persona que va a tomar la foto, entonces nada más vamos y rápido, ¿ok? Gracias. Y a los que están en externos, volvemos a las 11:30. Ok, nos vemos de regreso. Gracias. A ver. Ah, ya. Se oye perfecto. ¿No? ¿Me escuchan? Sí. Yo creo que sí me escuchan. ¿No? Pero no estoy diciendo nada. ¿Ahora sí? Sí. ¿Se escucha, Abraham? Sí. Súper. Retomamos ahorita que vengan los del coffee break. Supongo que los de las otras sedes ahí están. Ah, voy a apagar mi micrófono un momento. Bueno, ahora sí. Había que hacer cosas, ¿no? De logística justo antes de empezar, obviamente, pero ya estamos listos. Bueno, ya no me acuerdo ni qué es la presentación. Los dos micrófonos están aquí. Te lo paso aquí, mira. Ahí va a estar. Bueno, yo supongo que las sedes externas están ahí, sí, ya las veo, ya las veo. Bueno, empezamos. Bueno, ahora les voy a hablar sobre Time Series Observations, que es un observation mode con Jwst. Bueno, voy a hablar en inglés para no hablar todo mucho como hace rato. Entonces, today we're going to talk about the time series observations. And first, I would like to talk about what are time series observations. I personally think they're the best kinds of observations. And for example, they give us the light curve and spectra of a supernova. Here you can see it in this animation. And this is the light curve and how the spectra of the supernova changes with time once the supernova explodes. We can also measure information about the spots on stars. And this is also the light curve as a function of time. So the brightness is a function of time. And my particular interest besides the spots is it's the kinds of observations that you need for transiting planets. So in a more general sense, time series observations monitor time variable phenomena with observations optimized for detecting faint variations of flux over short or long time scales. Here it depends on what is the science that you want to do. There is a link to exactly what it's meant by time series observations for James WST. And here it is, the JDocs. Okay, so time series observations have been optimized for James Webb in different ways, mainly by instrument setup and data processing. So for time series observations, dithering is disabled. So basically for every other mode of observations, you need dithering. But in this case, dithering causes intrapixel systematic noise that doesn't enable us to get the precision that we need for, in particular, transiting planets. Target acquisition is enabled and is mandatory for most of the instrument modes where the time series observations can be done. This is so you can really choose where, in what pixels you are observing your stars, okay? And you make sure that that star is going to stay on those pixels. Exposure times can take longer than 10,000 seconds. So this is not something that we discussed yesterday or today, but every 10,000 seconds, James Webb needs to do a correction. So exposure times are limited by this. And normally what happens is that you cannot take exposure times longer than 10,000 seconds. But in the case of time series observations, you can do it, which means that during these observations, you get the high gain antenna can move. So that is the correction it needs to do. The high gain antenna is basically the way in which the telescope communicates with Earth, and it does this correction. It has a very small beam size, and it has to be pointed exactly at the Earth so we can receive all the information. So every 10,000 seconds, it makes sure it's pointing at the Earth. So in the case of time series observation, well, it's going to move the antenna even while we're doing observations. For the rest of the modes, it does it in between observations. Every integration is treated as an individual observation, and data are processed by a dedicated pipeline. So these are the modes where time series observations are possible. This is what they called in the JDocs a decision matrix. So you decide whether you need photometry or spectroscopy, and you decide what kind of wavelength range you want to observe, either at short wavelengths, so below 5 microns, or at long wavelengths with MIRI specifically, at longer wavelengths than 5 microns. In the case of the imaging, these are the NIRCam filters that can be used, because NIRCam is the one that provides the time series observations. And these are MIRI filters that you can use for imaging. All of this is in the pocket guide. For spectroscopy, we can use the NIRCam time series Grism spectroscopy and the single object slitless spectroscopy that we just heard about, as well as NIRSpec bright object time series spectroscopy. And in the long wavelengths, then MIRI low resolution slitless spectroscopy and MIRI medium resolution spectroscopy. Okay, these are the ranges of things that we can observe, but it must be said that in the case of the MIRI medium resolution spectroscopy, we can only have IFU mode, which is not suitable in particular for transiting planets, because has not been proven that you can get the precision that you need for the signal. The rest are more straightforward. Okay, so for precise measurements, we need to understand the noise. So there is a dedicated page for time series observation noise sources. The highest achievable precision is to reach the photo noise floor of the observation. That means where the noise budget is dominated by the Poisson noise of the source and the background. Okay, so the first two kinds of noise are the spacecraft pointing drifts and jitter, and this is also tightly related with the high antenna moves. This is exactly what I was talking to you about, which is that the drifts, what causes is that if you have an undersampled BSF, then the drifts are going to really change where the flux is received on the detector, and those changes of pixel to pixel changes are the ones that are going to introduce systematic noise to your observations. Basically, what we do normally is take flat fields to correct for this, but the precision with which you can correct this really depends on the quality of your flats, its stability with time, and we, in my experience, it is just better not to move the stars from the pixels, because the correction is not good enough. And then it's the high gain antenna that I already talked to you about. So every 10,000 seconds, there is going to be a jitter in the pointing. The other kind of noise is from the background, and this is particularly important for faint sources, of course, and for background limited sources. You are mostly concerned with the variability of the thermal background, which is basically what JWST is contributing to the background, and of course at the longest wavelengths. Then we have detector gain variations. This is the pixel-to-pixel gain differences, which you can correct with flat fieldings. And in the JWST detectors, it's of a few percent. But this is, of course, everything has been done on the ground. We'll see once it's there and what happens. And it will be better once it's in flight. Then we get intrapixel gain variations. These are changes within the pixel that se me olvidó la palabra. That respond differently. I found it. That respond differently within the pixel to the photons, and this has been characterized for Spitzer, for example, in the case of transiting planets in this paper. What we know before the launch is that JWST is better. So it's better in pointing, in sampling of the PSF, in astrometry, in the promotion of guide stars, and in the detector technology itself. So what the JDocs say is that we don't expect this intrapixel gain variations to be significant, but again, we need to wait until it's in space and we see how it does. And this is definitely something that will be measured during commissioning and characterized in the detectors. Okay, and finally, persistence. This is a memory effect. So if you observe a bright target, then there is some charge that is trapped in the detector, and this causes that if you're observing another object, the pixels that had the bright star or the bright object will remain with some charge, and this is also something that happens in infrared detectors, and that they will characterize later. The signal is a positive signal, so you keep charge, and it decays with time after you finish exposing the right target, of course. And this is exactly what I said before. Oh no, this is something else, sorry. Now, after we've spoken about the noise, then let's talk about saturation, because most of the targets, not most of them, but some of the targets that we're interested in the time series observation are bright targets. So then we care about how JWST handles saturation. So there's, again, another JDocs page about saturation. And what they have is all pre-flight and will be better characterized during commissioning. So what is saturation? In general, we think of saturation where photons are arriving on a pixel, then they stop counting. So normally, a photon is associated with a charge, and once you cannot create more charge, then we think about it as reaching the full well capacity, okay? In the ATC currently, all pixels are equal, even though they already have some information about how good each pixel of the detectors are, but this is what the ETC assumes. And they're set between 70 and 80% of the full well, okay? Okay, so this is based on the experience that they've had with Spitzer and Hubble. They know that this is a significant source of uncertainty, and once they get in-flight data, they will be able to better study this and correct for any systematic noise. But they expect that since JWST has much newer technology and everything, these will be minimized. So then let's talk about target signals for time series observations. For cycle 1, the recommendation is actually to go to 50% of saturation. So when you're exploring the ETC, like Omaira told us, and we expand all the integrations, then don't go for one below the saturation, but go well below the saturation. And this is because for time series observation, your signal to noise is not defined by your one data point, but is defined by the signal that you want to measure in the time that you want to measure, okay? If the ETC says that you're close to the limit, then you should reconsider having a higher resolution, so you're spreading the light in more wavelengths. You have smaller subarrays, so you can read faster, okay? Have also a faster readout mode, which is also related to the first, but it's not only that. As you remember, we had groups and integrations. And if you're taking spectra, whether the section of the spectra that you're interested is actually saturated or not. So you can live with saturating a part of the spectrum that you're not interested, as long as you can get the data that you want on the other side of the spectrum. These are definitely different recommendations than what we have listened to so far. Okay, and finally, they have instrument-specific recommendations, and I have just put the links to the JDocs there, and I will not go through them because we don't have enough time, but there's definitely the information. If you find an instrument mode that you want to use as a time series observations, then feel free to read this. So then, this is my personal bias, of course, which is the thing that I know the best. So we will focus on the rest of the talk mainly on transiting planet observations with James Webb. The first thing to do, and this is something we spoke about yesterday, is whether this object is observable by James Webb. And we use the general visibility tool. You already know what this looks like. This is for the case of K218. And you can see that these plots for visibility and the available position angles look very different as the ones that we saw yesterday. And this has to do because the closest you are to the ecliptic, the most restricted you are in position angle. You can observe the target for a longer consecutive time, but in the same position angle, and this is what we're looking at. So here, we're observing for almost, I don't know, how many months? It looks like 4 months. Yeah, but it has to be in a very, very narrow range of position angle. And of course, if you look at the RAN deck, this is very close to the ecliptic. This is a K2 target. So K2 was observing on the ecliptic. So this is not surprising that we see the visibility plots like this. Okay, so once we know that our target is observable by James Webb, then we need to know when the transits are occurring. In this case, we can use, for example, AstroPlan or whatever you like to use for your own. Normally, you have a time at which the transit occurs and the period, and you can calculate it for the range of epochs that James Webb is going to be observing. So what does it look like? Here we have each vertical line is the time at which a transit occurs for this object. And as you can see, some of them occur at times where the object is not observable by James Webb, and those are in red. And the ones in blue are the ones that do match with an observing window. In this plot, I just overput the lines. I actually grabbed this from another things. But you can grab, because you know that the general visibility tool gives you all this information about the windows that you can observe, then you can reproduce this and say, if I have these constraints on the satellite and I have these constraints on the target, then what are the observable transits that I can get? So for 11 transits during this time frame, only 4 of them are observable by James Webb. The third thing we need to consider is contamination by nearby sources. And this is especially important for the slitless spectroscopy. And we already had an introduction to this in the morning, but I'm gonna just talk about it briefly. And basically what you have is you have your transiting planet host and a companion that is really close. So then you need really the correct or the optimal PA angle or position angle, so that when you separate the light with the grism, then they're not overlapping. And what happens in a contrast is if you have a different PA angle, then you get this, okay? So this is something to consider when you're doing very high precision light variations, then there is no disentangling that you can do that is precise enough. The fourth thing, of course, and it's the most important thing, is that you need to do this in the APT visit planner, okay? So once you know that it's observable, and once you know when the transits occur, and once you know that you are not contaminated your sources that you're interested in, then you really have to put it into the APT, and that is the ultimate test of whether it can be observable or not. Okay, so here I'm going to go through one of these cases. This is an example of a science program. In this case, is the observation of the secondary eclipse of HAT P18. And we don't have time to go very slowly and to have it be a practical test, but you can definitely open the ETC and you can try to follow as I'm doing this. I'm going to go quite quickly. Otherwise, we don't have enough time to cover all this of the topic. So the first thing is that you need to set the scene and the source. We did this so many times yesterday. I'm just going to go ahead. Here, of course, is the ID information. I put in HAT P18. I am selecting a K2 star from the Phoenix Stellar models because that is what it represents for HAT P18. And then I do the renormalization based on a measurement in the K-band of this object that is 10.23. And I say that it's, of course, a point source. And then I'm going to plan the calculations. And in particular, in this case, we need to do the target acquisition. We include the area index of the object. And we say this is a time series or Grissom time series, okay, for the instrument setup. And in the case of the filter for the target acquisition, this is it's a fixed filter. We cannot choose it. So then we go to the detector setup. In this case, we choose a subarray, which is the smallest. This means that we can have the short X exposure time. And we also choose the rapid readout pattern. In this case, we have all these kinds of readout patterns. There is a JDoc that explains everything. But the rapid means that you don't skip any, and every frame is considered an integration, okay? So in this case, you have to put 1 and 1, and it's fixed for target acquisition, and then you can play a little with the groups. So then we already know what this means, which is the signal to noise at a given wavelength. And then, so what we want, in this case, it's telling us that for HAT P18, we're getting a signal to noise of 145 for the target acquisition. This is important because depending on how good this image is, then it will be the astrometric solution. And we want it to be about 100 or more, of course, to get a better than 0.005 pixels in the centroid of your target. Otherwise, if you have a signal to noise that is, oh, this one was smaller, obviously. I will fix it. Then your centroid accuracy is not as good. Okay, so then we already did the detector setup. Here we started we did the target acquisition just now. Then we do short wavelength time series, which is what we choose right here. We go back to the detector setup and make sure that we have what we need. The rest of the instrument setup, I summarize it here, but you know how to do this already, so there's no point in us doing it together. And this is what I was talking about here. You say the total exposure time is 0.55 seconds, okay? This is completely different than what we were doing with Omaira. But since we're counting one frame, one integration as one, then this is the exposure time that we have. And then we calculate how much time you need based on what you're trying to measure. If you're trying to measure a transit that is 2 hours, then you will have to observe exposures of 55 seconds for the entirety of the 2 hours, and then you know what is the number of integrations that you need. Okay, so in general, what you need to know and what you need to do is to adjust the number of groups. So here I just put a mouse in the center of my star, and it tells me that it's going to saturate at 13, right? And you can see in different parts of the source the pixel that it's going to saturate the fastest, or how it looks like. And remember that the recommendation from a CSI is to choose between 50 and 70% of saturation. So in this case, the group will be composed of like 7 or 8 integrations. Okay, so now let's set up the APT for our observations. We already have what we need from the ETC. This is also a guide. There's the link. We, of course, open a new proposal, all the things. You already know how to do this. We set it up in the proposal information. Then we set up the target. We include the RAN deck. Here, we are going to start the observations, okay? So in this case, it's NIRCam time series. We already gave it the NIRCam time series template over here. We then need to give it, an important thing to do in time series observation is to give it the special requirements, okay? You need to be as broad as possible to give the SCSI team the most flexibility in scheduling, but of course, that you can actually accomplish your science. The most restrictions that you put in your special requirements, then the more difficult it is to observe them. So in this case, for example, because we're trying to observe the secondary transit and we know when it happens, then we give it the phase range, we give it a period and a 0 phase, where it's acceptable for JWST to start observing your object. If we give it less than 1 hour in range, then you get an overhead of about an hour automatically. So then it's better to just give it a range. And you can do that. This is the recommendation, is that if you have a duration of your signal, then you give it a time that is equal to, this is in hours, 0.75 hours plus half of the duration of your object, or 1 hour, depending on which one is longer, okay? So this way, James Webb will start observing way before you need the observations. You allow it to have settling time on your object, which has been proven, for example, in Spitzer and HST, that is important to get really precise measurements of the object. And you make sure that you don't miss the transit that you're trying to observe, okay? So give it enough time so that you have flexibility for JWST to observe your object. Okay, so then after that is like the most stringent constraint, I forgot to mention here, this time series observation and no parallel comes automatic with the NIRCam time series template. Okay, so then, of course, once you've done everything, you need to do the visit planner to make sure that your visits are observable. And you need to click on Smart Accounting here. I had already clicked on it, so it looks like it's gray, and I couldn't click it again before I took the screenshot. And here you can see that there are constraints, of course, that give you visibility for the different restrictions. But in the end, your object is only going to be transiting on those tiny lines, and those are the times where you are going to be able to observe, in this case, the secondary transit. Okay. I hope I convinced you. The time series observations are the best. It's exactly on time. But as you can see, I had to go really fast to cover everything. There is definitely examples of science cases and of program observations that you can follow for the different kinds. Here, I just chose an imaging template or an imaging example because we had spoken so much about spectra in the morning, and I wanted to be a little bit different. Okay, any questions about time series? ¿Le pueden llevar el micrófono a Gloria, por favor?
why the no parallel constraint? Is that instrumental?
I think
So
so.
you cannot perform a time series in parallel mode.
No.
But while you're doing your time series, some other instrument? Oh, so no parallel
nobody can
mode?
observe in parallel with your observations.
So it's a very expensive type of...
Yes. Any other questions in Illinois, Morelia, Ensenada, si ya llegó? Creo que no estaban porque es muy temprano para ellos. Creo que no. Bueno. ¿Aquí? Sí, bueno, los que estaban en Ensenada.
Can you use a coronagrapher in time series
That's a
observation?
good question. No, creo que no. No estoy 100% no. Dice Joel que no. Él nos va a hablar de del high resolution. Sí, no. Yo no lo leí en ningún lado, pero ya dice que no, así que le creo 100%. Ok, ¿alguna otra pregunta? Sí.
O sea, al principio vi que se podía observar bueno, obviamente una serie de tiempo como esta, pero también una serie de tiempo de espectros.
Sí.
¿Hay alguna limitante? O sea, ¿se puede observar en el mismo modo o más o menos son los mismos tiempos de exposición o con qué?
No, para nada. Eso es completamente distinto y está en el Decision Matrix que les mostré.
Uh-huh.
Entonces, cada uno de estos modos de instrumentos y de observación tiene su templete dedicado en el ETC y que te va a decir exactamente qué es lo que necesitas. Yo les mostré específicamente un ejemplo de NIRCam Imaging, ¿ok? Sí. Y eso es específico de eso, obviamente no es exactamente igual para todos. Tendrían que ir a los JDocs y leer estos ejemplos. Aquí no está como link, pero aquí sí te dice, si tú entras a esta liga, es el Time Series Observation Roadmap y te da como vamos a hablar un poquito de qué son los roadmaps. Omaira les va a contar más, pero ya que estamos aquí, pues se los explico así a grandes rasgos, que es como las decisiones que tienen que tomar para poder observar de un cierto modo o con un cierto instrumento. ¿Alguna otra pregunta? ¿No? ¿Allá no dijeron nada? Ok, pues entonces vamos a la siguiente presentación que también me toca a mí. Y déjenme encuentro mi presentación. Y entonces, we're going to start with moving target observations with James Webb. Now this is the takeaway slide. The solar system is amazing, and we can explore it with James Webb. So the solar system moving targets, James Webb can observe the solar system with high sensitivity and spatial resolution through imaging, as well as low and medium resolution spectroscopy from 0.6 to 28.5 microns. There is a dedicated help desk card for the solar system and moving targets, and also for time series. Okay, I didn't talk about this in the other one, but there is. So the science requirements for moving targets when they were creating James Webb was that it had to be able to follow, because the objects in the solar system are so close to us, then they move really fast compared to the celestial sphere. So then James Webb must be able to follow an object with this rate of movement in the detector. This is really, really fast. It's basically 108 arc seconds in 1 hour. Okay. Normally, what is the rate in the celestial sphere? No, not yet? Okay, fine. I just want to talk briefly about the target of opportunity policy, which is there are two kinds. One is the disrupted TOs, and we spoke about them briefly in a question yesterday, which is if you have a 48-hour turnaround, then there is an extra overhead of 30 minutes automatically charged to your time, but only they are going to be limited to 8 TOs of this kind in cycle 1. The non-disruptive TOs have a 14-day turnaround, and there is no limit of those in cycle 1. So if you find an object that you want to follow, hopefully 14 days later it's still there and you can observe it. Okay, so what is the duplication policy? Briefly, observations of the same target. Well, no, we already went through this. I just wanted to say here that an example of encouraged duplication is an annual NIRSpec IFU observation of Jupiter's red spot, for example, and this is part of what happens if your object is changing with time. I want to know what happens. Well, this is an example of an acceptable duplication. And an example of discouraged duplication is duplicate observations of a small asteroid with NIRSpec IFU to increase the signal-to-noise ratio of a spectrum obtained already with JWST in a previous cycle. There are specific policies for moving targets, and specifically, for example, for the guide star, you have to add 90-second acquisition, but plus 30-second per dither. And I don't remember what this means. Oh, I remember. And if your observations are time sensitive, so if you want to observe, for example, an occultation of a Galilean moon or something like this, then you get charged an hour of overhead time automatically. So we have the specific moving targets visibility tool, and we already seen this a million times. What you need to give it is the designation of the moving target. And I will go through the optional things. This is a flag, and this is the only thing that you would need in principle is the designation. This is a flag when you want to distinguish, you give it a number. For example, in this case, if you put 4, it can be Mars. But if you're talking about asteroids, then it could also be Vesta. So if you want to observe Vesta, then you would put the small body 4 and the small body flag, and then you will get Vesta. Yes, okay. So this is what you would get if we run the moving target visibility tool for KBO. So it will give you basically what we already seen, which is what is the visibility in terms of the position angle and the different instruments. Again, these are more similar to that K218 that we saw in the example before in time series observations, because these are, of course, on the ecliptic, then they're going to be very limited in available PA angle. Another thing to keep in mind is that the moving target visibility tool does not take into account how fast the object is moving. It just knows where it's going to be, okay? So then you need to do a second step to see if James Webb can do it. And that is to go to the JPL Horizons website, which is looks like this. And you can give it as an observer location. If you type at JWST, then it will give you the James Webb coordinates. And this is something that they are going to be updating every 21 days. Okay, so it's going to be the most precise orbit of the spacecraft, and this for moving targets is super important. Then you will have to do this. You will say, I need solar elongation to be restricted to this range. And if you remember, in the first talk, I talked about the visibility. There was a range in solar elongation that was visible. It's exactly this. It's on the dark side of James Webb, but you cannot look at the anti-sun direction. And then you also need the cutoff for the angular rate, which is the 108 arc seconds per hour, which is as fast as James Webb can move to track your object. When you click on the generate ephemeris, then you get a table. It has a lot of information in the top that I didn't put because it's basically giving you all the orbital elements of the object. But the part that you care about is this, okay? Here I asked it for the date and the RA index, and this is the rate change in RA index that you would get for that object at a specific date. Also, there are times in between the range of dates that I gave it that are not included in this table, and this is when the object is not within that solar elongation restriction. Okay, once you decide that 1, it's observable, and 2, it moves slow enough that you can observe it with James Webb at some point, then you can go to the ETC. And in this case, we're going to do the sample workbook and science program. This one is for NIRSpec, IFU, and fixed slit observation of near-Earth asteroids. It's example 34, and here's the link to the ETC example, okay? So you go to a solar system and then number 34. Okay. In this case, we are defining one scene and one source. We want it to be in thermal emission, so we just add a black body spectrum. And we also want that source to have reflected light. So then we add a spectrum of the sun, okay? And this, they say that this G2V 5750 and 4.5 in log G is the one that is closest to the sun within the database that is already in the ETC. Okay, so then, no, okay. So then we go to the APT, we create a new solar system target. We fill in this. In this case, we want to observe a surface feature that is on Io, the Jupiter satellite, okay? So then what we do is we fill out this, of course, and then we need to start filling out this level 1 type and things, and I'm gonna explain what they are. Level 1 are targets that are in orbit around the sun. So that is restricted to planets, asteroids, comets, dwarf planets, of course, okay? In this case, because we want something that is on Io, then that Io is going to be a level 2. Well, okay, no, I forgot this. So to choose Jupiter, then you have to do a standard target. And then in the standard target, you get this, and you choose Jupiter from the standard target, okay? Once you've chosen Jupiter, here you see level 1, standard Jupiter, is that you already chosen your level 1 target. Then you go to your level 2 target, and those are the ones that are in motion around level 1 objects. So in this case, Io would be a level 2 object. So then we go again into standard target, and we choose Io from the list. Here is Io. Level 2, Io. Level 3 is our targets whose motion are normally described with respect to a level 2 object. So it's basically the next level of objects. And this means surface features on satellites or offsets of one of the satellites. In this case, we are going to choose planetography. So this means that we're able to give it coordinates on the second level object so we can find the surface feature, okay? These are defined by IAU standards. So we're giving it longitude and latitude in degrees. We now have a defined target, so we can go to the observations. Well, we need to plan the observations. Of course, in APT, the observing templates are the same for fixed and moving targets. This is important to know. And also, we need to talk about the solar system target windows. So once you're in APT and you go to we've defined the target and we go to the section in observations, then we get this new section which says solar system target windows. And it will have some default windows and you can add your own. But in this case, because it's Io, then it has windows that say not occultation of Io surface feature by Io from James Webb. So this means that if you want to observe something that is not being occulted by Io, then that you do not want the occultation, that you can choose this window, okay? If you don't want an occultation of the surface of Io by Jupiter, not Io this time, then you can choose the second window. But you can also choose not only occultations, but you can also choose. Oh, ya no sirve. You can also choose how far away this surface feature is from Europa, Ganymede, and Callisto, because those are the closest satellites to Io, okay? If you need it to be really far away, then you can say, I want it to be more than 10 arcseconds. Maybe you want mutual occultations of the objects, then you wouldn't choose these windows, okay? All of these that say default windows appear depending on the thing that you've chosen, but you cannot edit them and you cannot move them. You just have the option of choosing them or not. So in this case, well, it's exactly what I said. You choose whether the different windows, you want it within the window or not within the window. So it's basically a Boolean of yes or no, okay? We have specified specific windows in time given what is happening with the object in the solar system, and you can decide whether for your science you need to observe within the window or for your science you need to observe outside the window. Okay, in this case we choose not within, and it's not within an eclipse, okay? So then, okay. So in this case, we choose not within the window where you're eclipsing Io with Jupiter. Perfect. If Io is behind Jupiter, you cannot see the surface spot feature. Another thing to consider for moving targets observations is, again, the special requirements. And specifically, you can do timing requirements. So if you are trying to observe different modes or do first an observation of one part and then the other, you can restrict them and say, I want this observation to happen first and then the second one. And this is applicable for many instrument modes. This is just an example here. So here you say, I have all my observations that I have defined, first and second observations, and I want to schedule the second observation after the first observation. So this is, of course, a restriction. But when we're doing the smart accounting, it won't change the order of your observations to minimize the time. Oh, and this is the number of minutes. So the minimum number of minutes and the maximum number of minutes, you can change the units, of when it can do the second observation. Okay, so once we have the targets, we need to plan the observation. For the solar system target windows and special requirements, you can really fine-tune it to what you want to do, but you have to be mindful to not get carried away. And this is true for all of the special requirements that you use on James Webb. The more constrained you are, the hardest it is for you to observe, because it's going to place a big burden on the people doing the scheduling, and it's just going to make it harder to get your observations on schedule. Also, the tighter you do your constraints, you may incur in direct scheduling overhead, and automatically you will be charged more time for making the observations to constraint. And that's it. Questions from moving targets? No, nadie. Everything is so easy now because ETC and APT, you're done. You can do whatever you want. En el INAOE o Morelia, que están un par de extragalácticos, ¿sí? Ah. No, no hay preguntas. Ok. Bien. Y aquí tampoco. Bueno, está bien. Es que les quedó todo súper claro. Sí, allí. Ahí están todos sentados juntos. No tienen preguntas. Bueno, está bien. Pues ahí está. Vamos a la siguiente. Entonces, déjame apago esto para... Ahí hasta que se prenda el... Ahí está.
Ya, ahora, sí, ya.
Sí, y entonces vamos a cambiar de computadora. Déjame agarrar un teléfono.
A ver si funciona. Creo que mi compu solo tiene.
Déjame hago el truco de desconectar.
Sí lo había
el
agarrado,
HDMI.
¿no?
Sí, pero es que...
¿Y qué puntero tienes este?
Es el del medio de abajo. Ajá, que este
Sí,
ya
porque
no
se
funcionó.
llama.
No, ya se le acabó la batería. Ahí está.
Okay. Well. Yeah?
Yeah?
Okay. Well, hello everybody. I am Joel Sanchez. I work here at the institute here in Cebu. And today I will talk about high resolution astronomy with the James Webb Space Telescope. I want to say that I am not really expert on the coronagraphic mode, but I will try to do my best in order to explain you more or less the different modes that we can that we can use. First for the coronagraphy, and then for the sparse aperture masking interferometry, which is something that I am more interested in for my scientific purposes. So I know that all of you are astronomers, but I want to remind you some basic concepts. The first of those concepts is basically resolution, right? So the resolution that we have with a telescope is more or less proportional to the wavelength of the observations that we are performing divided by the diameter of the primary mirror in our telescope, right? So it means that at a given wavelength, if we build bigger telescopes, we will have more resolution. And resolution is nothing else than this ability that has our telescope in order to resolve or to separate two nearby objects in the sky, right? And that is in fact why we always want to build bigger telescopes, because we want more resolution to better distinguish some aspects in our image. On ground-based observations, this resolution is actually degraded by the atmosphere. So the atmosphere limits the resolution limit that we can achieve. And there are some techniques and some technologies, like for example, adaptive optics, that help us to mitigate this effect. So here is a quick animation or a simple animation where you can see a pattern of speckles, which is basically what you will record with your telescope, because the atmosphere is corrupting the wavefront that you are measuring. And once you activate the adaptive optics, you can see better the PSF of the object that you are observing. No? In this case, a point-like source. So, but this is on ground-based telescopes, but it's important for you to have that in mind, right? The other concept is sensitivity. So this is basically the smallest signals that we can clearly measure with our telescope, right? And it's basically the flux level, the flux that you have in your star or your galaxy, and then divided by the noise that you have in your image, right? In your record image. And then high contrast imaging, as I understand it, is basically an observational technique which aims at detect the faintest possible signal at the highest angular resolution possible, right? We want to detect a very, very faint object with the highest detail that we can achieve with our telescope or telescopes. We have several of them. So one technique that has been actually very fruitful during the last years is coronagraphy. And this is a technique that allows us to block the light of a given star in order to detect a much fainter object or emission around the star. And this is an animation that explains you how coronagraphy works. So basically, we have an object. We receive the light from that object. It passes through an optical device, right? And then for the object that is on axis, here, we put here a mask which blocks the light of the star in this case. So it blocks the light, And then it removes this contribution. And then, for example, if we have another signal, in this case, a planet, which is not on axis on the optical device, right? We will basically see that signal here in the detector. In this case, in this particular simulation, you are observing some speckles, which are basically contributions from your optical device, but also it could be from the atmosphere if you are observing from the on the Earth. But basically, you can correct this. In this case, they are using a default mobile mirror, which basically minimize the contribution of the speckles, and then you start to see with more detail the two planets here, right? It's magic, yes. But basically, the idea is to remove the contribution of the star that outshines more fainter targets or emission. It's as simple as that. But there are many ways in which we can design this mask here. So the simple case is basically annular, no? We put in our optical device in the optical axis something that blocks the light, right? But during the last years, particularly for ground-based infrared cameras, like for example, Sphere at the BLT or GPI, the Gemini telescope, there has been a lot of developments of different types of coronagraphers, right? That not only blocks the light, that basically disperses the light. They send the light of the on-axis object to the outer part of the pupil, and then it is removed or it is blocked. So some examples of those masks, of those coronography masks, are the 4-quadrant phase mask, which basically creates interference, destructive interference between the light of the on-axis target, and you remove that. You remove the core of your PSF, and this is more or less what you get in your pupil here. And there is another mask which has been actually quite interesting in detecting exoplanets with the Sphere, which is this annular growth phase mask, which induce differential delays in the phase of the signal, in the phase of the light that passes here, and it basically helps to remove most of this light when it reaches the detector. So this technique actually helps us to detect the very faint objects. So in contrast, is 10 to the 4 or 10 to the 5 compared to the brightness of the star, of the host star. It has inner working angles. It means the smallest distance from the stars, which you can actually measure the signal of the planet or your faint emission, which goes of the order of lambda over d. This is actually the ideal case, okay? But it also has a very complex data reduction. So also during the last 10 years, there has been a lot of developments of new techniques on how to reduce coronographic observations. Now, and this is just one example of how you can, for example, post-process coronographic observations. So you observe the target different times over the time, right? Then you model the PSF of your target using a principal component analysis in this case, right? You remove this model or you subtract this model from your observations. And since you are only modeling, for example, the PSF here, the planet will remain in your residuals in this case at different position angles, because this is, of course, rotating. And then you can derotate all your images, you stack the images, and you can finally see the signal of your planet. So this is something, for example, this technique is called principal component analysis plus angular differential imaging. But this is post-processing for this kind of observations. So you just need to take that into account. But coronagraphy is it has been very important for detecting exoplanets. Like for example, here where you can see at least 3 planets orbiting a star. You can see here in the middle, this hole is because it is basically the coronographer nulling the star. You can also detect disks or see with better detail disk around young stellar objects. These are all sphere images of different stars. Or you can detect a combination of both, like for example, in this case, where you detect a planet here, and then you detect a jet or an outflow component in this direction. So it's very, very interesting. In this case, in all of these cases, your angular resolution is of the order of a few milliards seconds. Well, not a few milliards seconds, let's say 100 milliards seconds or so, which is really high angular resolution. Most of those images are in H-band, or in the infrared at 1.7 microns or 2.2 microns, something like that. No, it's H-band or K-band. So the James Webb will actually offers different coronagraphic modes with two different instruments. So there are 5 implementations of LEOD coronagraphs, which are basically these nullers, right? 5 in NIRCam and 1 in MIRI. There is 4 quadrant phase mask coronagraphs, 3 in MIRI. And then there is this particular case, which is not a coronographic mode, but an interferometric mode called sparse aperture masking, which is implemented on NIRIs. So probably you already have seen this image, but basically is the wavelength coverage of the James Webb for the different instruments. So you have here the instruments in the near infrared, and then you have MIRI for the mid infrared, right? So in this case, NIRCam works in the near infrared from 1 to 5 microns, more or less. And you have here just a schematic of the instrument. And here on the bottom, you have the 5 different masks, the 5 different coronagraphs that you may have there. So there are just three nullers here, circular nullers. And then you have 2 striped bars that can also act as coronagraphs. So basically here you are blocking the light on a given position angle, not only on the star, but on the whole position angle at which you are placing this mask here. So this is the transmission curve for NIRCam, for the coronographic mode of NIRCam. And what I want to highlight here is the fact that although NIRCam works from 1 micron up to 5 microns, for the coronographic mode, it only works optimal above 2 microns. And this is basically because the transmission for the coronographic mode drops considerable below 2 microns here. You can see that here, right? So you have 3 coronagraphs that works at 2.1, 2.5, and 2.1. Sorry, there is a mistake here. It's 3 microns. And these 3 are the nullers. Okay, and then you have the nullers have 6 lambda over d inner working angle. So this is the smallest distance that you can approach to the central star or to the host star. And then you have in green here 2 additional mode of observations, which correspond to the stripes that has inner working angles of 4 lambda over d. Okay, so this is basically broad filters for the green ones, and then you have narrow filters for the red ones. This is a contrast plot. So you have here separation versus the contrast ratio for 5 sigma detections that you can achieve with the coronographic mode. This applies for NIRCam and also applies for MIRI, for the LEOD coronagraphs. So with no coronography, this is your contrast limit. With the coronography only, you reach this contrast limit. But then if you apply 2 additional techniques to improve the subtraction of the PSF and the residuals in your coronographic observations, you can actually achieve these 2 limits here. So it's basically at 2 arcseconds, you can achieve a contrast of the order of 10 to the minus 7 compared to your star. So this is MIRI. MIRI works from 5 microns to 25 microns. It's actually a large range for this instrument. Sorry. You have 4 quadrant phase masks here. So this is the schematic of how they are placed in the instrument. They are working at 10.6 microns, 11.4, and 15 microns. And then you have a Lyot coronagraph that works at 23 microns here. You have here the filters. Again, you have three different coronagraphs for, let's say, narrow band filters, and then one coronagraph for a much broader or large band filter. And these are these are basically some observations, some simulations of how you will see through the coronagraph at the different with the different ones for the different filters. So for the coronographic mode, at least here in MIRI, you crop your detector. So you are not using the full detector. You are just using a piece of that. So you have here the field of view, 24 arc seconds, 24 arc seconds, and here you have 30 arc seconds. Okay. And here is again the same contrast plot. So separation in arc seconds, and here is contrast at 3 sigma. Forget about all of this. The important thing here to notice is that you can achieve contrast ratios between 10 to the minus 5 and 10 to the minus 6 for the coronographic mode in MIRI. So it's really considerable. So, but now I will pass to something that for which I am more interested in, because this is something that I have been using for my own science, and I think it's a very interesting mode for the James Webb, because it's going to be I think this is going to be the first time that there is an interferometric mode in a space telescope. This has not been before there. And although it's a trick because we don't have multiple telescopes, we just have one, it's a very important technique. So I wanted to highlight that at least I am part of a team that has one of these early release science programs to study dust production in wide-rayed stars using the sparse aperture masking mode of the James Webb. So basically, there are these kind of objects called pinwheel nebulas, which are produced by the wind collision between two stars and the rotation, of course, of the binary in the center. And I'm observing one of those targets, which is WR140. I don't know why the 140 is not here. Which is, you have here the two stars, and then you have shock fronts of the dust produced that is actually moving away. And we want to observe all the faint diffuse emission here in this region for this object. And then we can compare this with basically models on how the dust is produced and what happens in the shock front between the two, the winds of the two stars, right? So the interferometric mode of the James Webb is installed on NIRIS. This is NIRIS, and here what we do is that we place a mask instead of nulling the star or nulling the light of a star. We place a mask with different holes, with several holes in the filter wheel of the instrument. And actually, I bring you here a couple of those masks. These are masks manufactured for the James Webb. So this mask has the actual size that will be placed on the telescope, or that is placed on the telescope because it is already there. So you cannot remove it. But this one is the final design. So these two masks were manufactured for doing tests and prove different results for the interferometric mode. So you can see them, you can open them, you can touch them. I mean, it's just a very thin piece of aluminum, and then you have the different holes there, which are very precise there. So you have different filters here. You have 4 different filters that you can use for the aperture masking mode: 2.7 microns, 3.8, 4.3, and 4.8 for the observations. So as I said before, this is the layout of the aperture masking. So you have a mask with several holes that you put in the pupil plane of your telescope, and then in the infrared camera, you record something like this, which is not a star or an object. It's an interference pattern, and this interference pattern is actually produced by the geometry of the mask, right? So every pair of holes in the mask produce a set of fringes at different positions and orientations, and then you combine all those fringes, you produce this pattern here, and if you are observing, for example, some extended object, this pattern is convolved by the actual brightness distribution of your object, which is the advantage of using something like this that produces a complicated pattern in your detector instead of just going and observing directly your star. With basically, you have a very well-defined PSF, and then you achieve a resolution that is 2 times better than the diffraction limit of your single telescope, right? So you are sampling very specific spatial frequencies, which means that you are only sensitive to some angular extensions in your object, right? But you can still recover the brightness distribution after some complicated post-processing, I would say. So my question here is, for example, if you observe an object, let's say a disk, a star with a disk like this one, and you record something like this in your detector, how you move from here to recover actually the brightness distribution of what you are observing. What we do, and this is something in which I have been working on, is basically to fit the fringes in the image plane. So basically, since I know all the contributions from the different pair of holes in the mask, I can remove them and basically isolate the interferometric observables for the star or the object that I am observing. So in this case, for example, if the object is asymmetric, it will induce some shifts in the fringe patterns from a given reference position that I know. And of course, if the object is extended, it will decrease the contrast between the different fringe patterns also. And I can actually account for this and try to retrieve the interferometric observables from there. There is a quantity that we use in this kind of observation called the closure phase. And this basically helps us to eliminate the pinholes dependent errors. This is a trick that we use for this. So basically, we multiply the visibilities over a closed triangle of baselines here, and then we end up with a quantity that depends only on the brightness distribution of the object, which basically helps us to measure the asymmetry of the object. So if you use this mode and you process your signals, you will end up with some plots like these ones. And if you have done interferometry before, you know what those plots are. So basically, you have here visibilities versus spatial frequencies, and phases or closure phases versus spatial frequencies. It's important to mention that you need to calibrate these observables because you need to take into account the transfer function of the instrument or the telescope plus instrument. And for this, you need to observe a point-like object, a calibrator, close to your star. And then in this way, you remove the contribution, the instrumental contribution for these observations. On ground-based observations, you also remove the contribution from the atmosphere. But in the case of the James Webb, since we don't have the atmosphere, we just have to deal with the instrumental transfer function, and it's relatively easier to remove. Okay, but you need to take that into account. So you observe something, you record this in your detector, then you post-process your observations, you end up with your observables. but still you want to go back to these kind of images, right? So in order to do this, and this is I think something quite novel, still under development, and I think this is my opinion, but I think this is something in which we can actually contribute, because there are only very few people doing this right now, because I mean, there are not really a lot of people trying to deal with this kind of observations, but it's basically the image reconstruction part, right? So how do we move from here to here, not back to the images? So here are some simulations on how we are recovering the image, which basically does not resemble completely this, because this is still affected by the fact that we have sparse UV coverage. No, we are only sampling a few spatial frequencies, and then we don't have a complete information, right? Well, but this is a problem that is actually now a hot topic in the community, and I think this is under development. It does not require a lot of investment, right? We don't need to build an instrument for this, but we can do software to do this, and this can be a great contribution to the field, and of course to the future observations with the James Webb. So how do we recover this? Well, in this case, we use something called regularized minimization algorithm, in which we basically try to minimize this expression here, which contains two main, or it has two main components. One is the likelihood, basically the classical chi-square. So we have a model image, we transform that into the Fourier space, we obtain the visibilities that we got with the mask, and then we compare them with the data, right? Plus plus this term here, which is this term here in the middle, just simply weights between the two terms. So because this will always depend on some prior knowledge that we have about what we are observing. And since we, for example, want to discover something new, then we may bias the final image. So how do we deal with this is actually what we are trying to achieve, you know? To find the best possible way to introduce regularization functions here without biasing so much the result, and basically creating all a complete framework of how to do this, right? So there are already some software available in the community to perform this kind of minimizations and recover images, and you can use the different regularization functions, but not all of them are actually characterized, and there are still a lot of work to do here. One novel technique that can be applied to this kind of reconstruction is called compresensing, which is an iterative process based on these three main concepts, which is an incoherent sampling. This is what we have already because we have non-redundant baselines in our mask. Then we transform this into a different base, and then we iterate over this process until we recover more or less the image. So these are some simulations using the UV coverage of the James Webb here, the 21 baselines that we have. We model different structures, different disks. We put this disk on something called a dictionary, and then we try to minimize this expression to go back to the visibilities and then to the images. And these are basically reconstructed images with different hyperparameter values. But we achieve to recover more or less the image in this case, which is an object, right? But still, if you look carefully at the images at the back, there are some residuals, and we still need to deal with those residuals. I forgot to mention something. When we do these kind of observations on the Earth, we basically can increase the UV coverage because we let the Earth rotate, right? And then we are sampling the different spatial frequencies over different hour angles, right? For the case of the James Webb, this is a problem because we cannot rotate the mirror. No, I mean, there is a small roll that we can do, perhaps 5 degrees, 7 degrees, I think is the maximum. but we cannot do more than that. So we have a very sensitive instrument because it is not affected by the atmosphere, but we have only a few spatial frequencies. So this is I mean, we need to deal with this in order to recover images, okay? We cannot mitigate the fact that we have only a few baselines with rotation, right? So if we achieve to recover the images here, then we can, for example, detect planets, but this mode is not only suitable to detect planets, it's suitable to actually image faint diffuse emission. In fact, if the emission is not symmetric, is asymmetric, is better, right? So this is the contrast ratio, 10 to the 4th, 10 to the 6th. It also solved the saturation problems for bright sources for the James Webb, right? Because since we are covering most of the pupil of the telescope, we only have between 10 and 20% of throughput of the light. So we can actually observe brighter objects. And then these are some scientific cases that we can try to do with this mode, no? Dust in YSOs, well-rayed stars, planetary nebulas, AGBs, AGNs, and also planet detection. It's complementary to coronagraphy because the inner working angle in coronagraphy is lambda over d, in the best case, no? You already saw that some of the coronographers have lambda, 4 lambda over d or 6 lambda over d. With this, you have an inner working angle of lambda over 2d, okay? So it complements the parameter space. And this is all from my side. Thank you very much. You have a lot of questions.
Por aquí, bueno.
Bien. Bueno, yo. Sí, entonces, una pregunta corta de lo que dijiste al final. Si con el James Webb tenemos una gran sensitividad, pero tenemos el problema del coverage de visibilidades. ¿Cómo uno podría entonces justificar el uso del James Webb? Porque estaba mirando los diferentes instrumentos que hay, por ejemplo, en la ESO, y con esto, bueno, podemos alcanzar una sensitividad que es decente, vamos a decir. Entonces, ahí habrá como para justamente esos tipos de ciencia, de coronografía, de alta, todo lo que es de alta resolución, ahí va a ser un poquito complicado para justificar eso. Si no, podría ser la banda a la cual uno está observando, pero en términos de lo que uno puede detectar, quizás va a ser un poquito complicado, ¿no?
Por ejemplo, para el aperture masking, la sensitividad de James Webb es muchísimo mejor que la que tú tienes con Visir en el VLT, en el infrarrojo medio o con Sphere. Incluso con estos sistemas de Extreme Adaptive Optics, es mucho mejor el James Webb. Porque aunque tengas el Extreme Adaptive Optics, siempre vas a tener efectos de la atmósfera. Incluso aunque las correcciones sean del orden de 100 actuadores o más de 100 actuadores, todavía vas a tener residuos. En el James Webb tú no tienes eso. Entonces tú tienes que preocuparte solamente por la calibración de tu sistema óptico. Pero el problema aquí es la limitante de que no lo puedes rotar, ¿no? Entonces tienes pocas frecuencias espaciales. Pero, por ejemplo, tú con Sphere nunca vas a poder, con Sphere y el Aperture Masking Mode nunca vas a poder detectar planetas. Tu sensitividad solamente te da para detectar brown dwarfs, por ejemplo. Con el James Webb tú sí puedes detectar planetas. Ajá. Aunque tengas el problema de solamente las 21 visibilidades, pero sí puedes detectar planetas. Y, por ejemplo, en el caso de planetas, en realidad no tendrías que reconstruir la imagen porque los puedes modelar paramétricamente en el plano de Fourier. La cosa con la imagen es más para las emisiones extensas, ¿no? Los objetos extendidos. Y ahí también la sensitividad es mucho mayor aquí que en ground-based observations.
visibilidades. Ay, perdón. Estaba diciendo que para planetas sí, pero no todo el mundo busca planetas.
Sí.
Entonces, para discos, por ejemplo, ahí a lo mejor vas a necesitar una cobertura mayor.
Eso es lo que aún estamos tratando de caracterizar. ¿Qué tanto podemos recuperar la imagen y el contraste entre la imagen? Nuestro principal limitante ahora mismo es recuperar imágenes realmente de alto contraste con este tipo de datos. Entonces, este programa del IRS, en realidad lo que intentamos es recuperar la imagen de alto contraste para un objeto que es extenso, ¿no? Que sabemos que tiene estos arcos que se están moviendo, pero creemos que hay emisión difusa mucho más débil que no vemos con visir, por ejemplo, que sí podríamos detectar con el James Webb. Pero el problema ahora mismo que tenemos está en el algoritmo de reconstrucción.
Ayer intenté calcular las visibilidades de un objeto en la nube menor de Magallanes usando el coronógrafo. Y la respuesta fue, there are no visibilities available for this configuration. Entonces llegamos a la conclusión que se debe a que hay ciertos ángulos para los cuales el coronógrafo no puede ser utilizado.
Sí.
¿Es lo mismo aquí?
Sí, seguro, sí. De hecho, hay muchos recursos en la página del James Webb. Está el ETC, ustedes pueden calcular ahí los tiempos de exposición. De hecho, hay secuencias específicas, al menos para el modo de coronografía, de cómo hacer las observaciones, ¿no? Te dicen, observa la estrella a un ángulo de posición, después rótala 3, 4 grados, obsérvala otra vez, observa una PSF de referencia para que la puedas sustraer, etcétera. Todo eso viene ahí. Eso es más o menos estándar. Sí hay algunos objetos que no se pueden, no se van a poder observar, al menos para ciertas épocas del año o que van a ser limitado la observación. Para el caso de la interferometría todavía está en desarrollo. De hecho, el ETC creo que no tiene cálculos para el interferometric mode. Este es todavía un poco non-estándar.
Pero la conclusión es que no se puede observar nada en las nubes de Magallanes con estos métodos.
Esto no lo sabría decirte. Así, al 100% no. Tendría que revisarlo.
Gloria, yo creo que podemos preguntar al help desk ahora a la hora de la comida, ¿no? Es una buena pregunta.
Ok.
Sí, pero ese sí no sabría decir.
Nunca mencionaste nada sobre cómo usar las nuevas propiedades de estos detectores, por ejemplo, los groupings, los tiempos de integración. Cuando estás muy cerca de un objeto que está cerca de saturar, debe de haber algún modo de hacer más eficiente la observación en modo coronográfico, por un lado. Y la otra pregunta es, ¿hay manera de hacer parallels cuando estás en modo coronográfico?
No, me parece que no. De parallels no estoy muy seguro. Y lo de la saturación sí es un problema, pero en realidad las recomendaciones que te da es que trates de ver si tu objeto alcanza una señal a ruido y si realmente está sobre el límite de saturación, trates de evitarlo, ¿no? De buscar objetos que no estén cerca del límite de saturación porque no los vas a poder observar. Lo más probable es que saturen. No, como te digo, para el Aperture Masking Mode todavía no hay muchas cosas que todavía no están establecidas, pero es seguro que con este método puedes observar objetos más brillantes simplemente porque tienes el 10% de la luz.
Hola, gracias. Oye, los radioastrónomos se han preocupado por este problema de reconstrucción de imágenes hace mucho tiempo. Están hablando con ellos.
No, ellos hablan con nosotros.
Ellos, sí.
No, sí, los radioastrónomos tienen ese problema. Sí. En realidad, ellos ya lo resolvieron de otra manera. Básicamente van y ponen más antenas. Ajá. Pero el problema está ahí. De hecho, ese es un problema muy tan actual que en realidad es uno de los el Event Horizon Telescope tiene 4 o 5 grupos de imagen trabajando en eso, porque realmente están tratando de desarrollar algoritmos para arrays que tienen solamente unas pocas antenas o baselines y que tienen exactamente el mismo problema que nosotros tenemos aquí, ¿eh? ¿Cómo recuperar una imagen sin que esté demasiado bias del objeto que están observando.
Sí, no, yo estaba pensando en ellos justamente. Tienen muy poquitas antenas, han desarrollado muchos algoritmos. Digo, qué bueno que estén en comunicación. Y ustedes, por ejemplo, acá tendrían el problema también de los radioastrónomos de que necesitan llenar el UV coverage, ver con un single dish, o sea, sería importante para este tipo de observaciones complementar con una sin las rejillas. O sea, esto, mira, es que no sé, los radioastrónomos para recuperar todo el flujo necesitan observar con un single dish, porque los interferómetros pierden flujo, ¿no? Entonces siempre tienen que complementar la observación del arreglo con un single dish, ¿no? Si no, no saben lo que es el flujo total. Si no les importa esto, sino nada más cómo se ve el asunto, no lo tienes que hacer, pero si no, quizá tienes que complementarlo con una observación.
Olvidé mencionarlo, pero con el Aperture Masking o sea, llevas una imagen en modo normal, una imagen, digamos que con la pupila completa, imagen directa, asociada a tu interferograma.
Ok.
Sí, pero incluso del interferograma puedes calcular el flujo, no hay ningún problema.
Gracias.
Tengo un comentario, una observación. Me parece interesante porque es como un modo de observación atrevido, ¿no? Esto último que estás diciendo. Es decir, todo el taller nos han dicho que todo está súper controlado, va a haber un pipeline, los datos van a estar ahí. Y ahora vienes y nos dices que esta observación solo sirve para fuentes puntuales, realmente. O sea, un poco es lo que estás diciendo. La reconstrucción todavía no se sabe bien a bien cómo va a ser, aunque has mostrado indicios cómo va a ser, etcétera, pero está en desarrollo, ¿no? Y la pregunta es más o menos por ahí, es un poco como el James Webb yendo a observaciones que todavía no está controlado, digamos, la reducción de datos.
No, yo creo que al final, hay gente que está trabajando para integrar el Aperture Masking en el pipeline completamente para que tú puedas obtener visibilidades calibradas del pipeline y después hacer la reconstrucción de imágenes. El punto es que todavía, la reconstrucción de imágenes está en desarrollo, pero no es un caso particular del James Webb, es que está en desarrollo para el VLTI, para Sphere, o sea, para el VLT, para el GPI, para muchos otros interferómetros en el infrarrojo, ¿no? No es un caso particular para esto.
Okay. Gracias. Otra parte de la historia que es súper importante es que también eres capaz de modelar la PCF en distintas longitudes de onda, ¿no? Y ahí, ¿cómo está el desarrollo? ¿Qué tan bien la conocen o qué tan bien caracterizada está?
Eso en realidad no es tan complicado aquí porque, como te digo, los residuos que tú tienes, o sea, los efectos que tienes sobre tu PSF, nada más están asociados a tu sistema óptico y se conocen más o menos, se tienen idea de los pistones, de cómo afectan diferentes baselines, de más o menos los rangos, etcétera. Ese no es tanto problema. Se pueden hacer simulaciones muy precisas. Hay software que se está desarrollando para eso. De hecho, creo que hay software integrado ya en PSF Web para hacer simulaciones de este tipo. Sí, ese no es un problema en realidad.
More questions? ¿Más preguntas?
Me imagino que de otra manera, me imagino que podrían hacer librerías inmensas de morfologías, ¿no? También para poder hacer alguna especie de trabajar esto con AI, ¿no? Por ejemplo.
Sí, de hecho, parte de esta idea del compressed sensing es justamente algo así, ¿no? Tú haces un diccionario con diferentes morfologías y después empiezas a comparar con tus datos a ver cuál de esas son las más probables que recuperen tu imagen. Eso también en algún momento podría servir para descartar modelos de objetos que tú estás observando. Tú puedes simular la física en un modelo, otra física en otro modelo y después tratar de recuperar las imágenes y a lo mejor puedes descartar completamente un modelo. Eso sería genial al final de cuentas que se pudiera hacer, ¿no?
¿Alguna pregunta más? Sí, así.
Bueno,
Muchas gracias, Joel.
pues muchas gracias.
En lo que se instala el siguiente, les quiero recordar que a la hora de la comida, durante 2 horas, vamos a tener el Help Desk en vivo con Space Telescope Science Institute. Apunté algunas de las preguntas de ahorita. Me gustaría que los que tuvieron dificultades con Aladdin me dijeran qué tipo de máquina o qué OS están usando y cuál era el problema para poderlo reportar, a menos de que ya lo hayan resuelto. Entonces, vengan conmigo, por favor, antes de irse a comer para que yo pueda hacer las preguntas y les vamos a dar luego si quieren se esperan a que nos den la respuesta o se las dan. Perdón.
De hecho, esta presentación va a ser un poquito corta, entonces entre que termine Omaira y las 2 para salir que va a estar lista la comida, vamos a tener tiempo justo para esto. Entonces, podemos discutir cuáles son las preguntas que tienen y asegurarnos de que las podemos hacer, ¿no? Aprovechen, como por ejemplo que el Moving Targets Visibility Tool no estaba funcionando, cosas así.
Okay. This is going to be a very short talk. Like 15 minutes or so. No necesito, ¿no? Let me quit my email so you don't see my emails coming. So the idea of this last talk is to highlight the fact that there is a roadmap for every mode. And what is the importance of that is that I think you already have understood that every mode is very special and it has a lot of information that you have to follow. And in order to make a proposal, there is a lot of considerations to be taken into account. Let me read what the web page says. So roadmaps are articles on the methods and intricacies of space-based infrared observing with James Webb are available to provide guidance for creating sound observing programs. These include example science programs and recommended observing strategies. I think the keyword, also difficult to read, is that this thing that all the modes are very complicated, some more, some less, but in each of them, there are a lot of suggested different ways to observe. So for a single instrument, but a different mode, there are different recommendations. No? So this roadmap, what it's trying to do is breaking your process into small steps so you can fulfill everything without feeling overwhelmed. Yeah, that's a good. So because every mode has their things, there is one of these roadmaps for each of the modes. Essentially, my idea is what you should do right now is to start reading the documentation on the instruments and on the different things that you have to learn, like the tools and everything. This is, I said at the beginning. Then the next step is to decide which is the instrumental mode that you are more interested in. And after that, what you have to do is to read the documentation on the modes, on the instrumental mode that you want. And as a third step, you will have a look to this roadmap. And the roadmap will tell you each in small steps what you have to do. So I put here an example of one of the modes, target of opportunity. This is the general information of the mode. So it says what distinguishes a TO from the time constraint or the time critical observations.
what are the observing constraints for a TOO? How do you activate and approve the target of opportunity program? Requesting this activation, what you have to do in order to request the activation, and evaluation and implementation. So the first thing is to know what is the difference between a TO and a time constraint. I have put here, many of you already know that, but just remind that in a TO, the main difference is that you don't know when it's going to happen, the event. So X-ray binaries, GRBs, are TOs. X-ray binary are supposed to go into burst, but you don't know when it's going to happen, the burst. So that's a TO. Eclipsing binary stars are no TOs. So that's the answer. Because they are time constrained, but you don't have to wait until something happens. You know what the event that doesn't have this kind of issue. Also, I put here gravitational waves, like a TO, but this could also be a direct or discretional time. This is something so new, so amazing that you could ask directly to the director to ask for one of these observations, and this is another way to do it. Yes. This is something that Gillian already covered. So TOs, observing constraints for TOs, there are two kinds. One are non-disruptive TOs for the schedule purposes, and the other one are disruptive TOs. Essentially, if you want to observe something right now, that's going to disrupt the schedule. So this is going to give you a charge on half an hour extra because you are doing something wrong with the telescope. And then it says how you activate the TO, add all the observation details, and then give to STSCI a way to reach you any time. And after you submit your activation, you should contact the program coordinator to verify it has been received by STSCI. And there is a web page where you put your ID, the ID of your proposal, you go inside, and this information is where you put it. Something that I found in the documentation is even if you have an approved TO, STSCI evaluates if the TO interruption of the schedule is worth it. So even if it is approved, sometimes they say, look, I don't care. I will go on with what I was doing. It looks to me that the TOs, that James Webb is not in the mood of doing much TOs, but perhaps it's just my impression. I'm not an expert on TOs. So after you read all this documentation, there is these baby steps that you have to do in order to prepare your proposal. So in this case, it has three different sections. First of all, preliminary considerations. And it says some information like if the target could be a known target and some consideration of what is a TO or not, to be sure. It says that in the PDF that you upload, you should say what trigger mechanisms you will use in order to activate your TO. And also understand what are the fluxes that you are expecting and the limitation of your observations. And then proposing a TO is something like that. So choose your instrument. And these are the baby steps I was talking about. Understand what filter or ratings are needed, and any other instrumental setup information. And then in the second step, you go to ETC. In the third step, you go to APT. And then you fill up the observing templates in the APT, estimates the total resources of your proposal. This is because sometimes you don't want to just do a single observation, but several of them over a certain time. And after that, there is some other things that you have to fill up in this case, like request custom time allocation. And then you write the proposal, upload in the PDF, and submit. That are the steps that you have to follow. But these are, well, then information on the activation that actually overlaps with the general information of the TO, so I won't repeat that. I just wanted to put some other examples to show you how different they are. For instance, James Webb Slit Spectroscopy starts asking you to choose which instrument you wish to use based on the wavelength range of interest. So it's very simple. Roughly, if you want to make a spectrum below 5 microns, you use one of them. If you want above 5 microns, is the other one. So that's why I was saying to you that this is very useful because it split such a huge amount of things in very little steps that you can deal with. And this go on with APT, ETC, and so on, upload and submit. But it has a lot of few steps, like selection of the dithering, this kind of stuff, no? And I also put this one just to show you that the life is not so simple. And in this case, you have up to 17 steps per your submission. So, but each of these steps are, they give you the links to the information that you want to require, that you have to read in order to understand what you have to do. So in summary, and that's the end of my talk, keep calm and follow the yellow brick road. The key is to just select a fan crew to make the trip. And as much as you will appear safe at home, hopefully. So thank you very much.
Questions, preguntas sobre el roadmap. Es como una receta para que no se te olvide tomar decisiones.
Another thing that I forgot to say is that my impression is that these roadmaps are changing. They are giving more information. Some of them are very with a lot of detail. Some others, it seems like they are less. They are made with less care, I would say. So hopefully, in a way, they will update them.
And also, this is why the date at the end of the JDocs page that tells you when is the last time that it was modified is important.
That's very important.
Especially if you have been, you're familiarized with a roadmap now, you decide on your object, you go, and then at the time of submission, or close to the time of submission, you realize it's a different roadmap. It's definitely worth looking at the difference.
Sí. Pero una pregunta, por esos cambios, imagínate que, bueno, haces todo tu camino, ya estás sometiendo, sé que puedes cambiarlo hasta que la fecha termine, pero no va a haber cambios grandes porque el tiempo de rehacer todo sería, ok, vale, simplemente para asegurarse.
De hecho, como habíamos dicho antes,
lo que espero es que estos roadmaps se complementen y se amplíen para que la información esté más completa.
Sí, más que cambiar completamente.
Sí.
Además, no es obligatorio seguir el roadmap. O sea, es una sugerencia.
Pero es altamente recomendable.
Pero sí que te da un lugar en donde empezar. Entonces, yo sé que hasta ahorita les hemos dado muchísima información en estos 2 días y bueno, ya hay cosas que ya saben, como IPT, ETC, ya entran ahí, hacen lo que tengan que hacer, pero rápido. Pero cuando estén pensando en su caso científico y en sus observaciones en particular, pues van a ser diferentes para cada uno de nosotros. Y entonces sí que el roadmap les ayuda a no perderse en el camino y decir cuáles son las consideraciones que tengo que tener para que mis observaciones sean factibles y que sean útiles para mi ciencia. Y creo que eso es lo más importante del roadmap.
Y ahí hay sugerencias. Hay cosas como selección de dithering, ¿no? Y te pone en summary. Creo que, de hecho, aparece un ejemplo bastante bueno aquí. A ver si soy capaz de encontrarlo. Sí.
Dice...
Choose editor pattern. Este no sirve, pero este sí. Mira, aquí está el... Aquí.
For MIDI, you should use full subarray in the APT to ensure la. If the spectral is what I'm saying is, lo que le estoy diciendo es que hay, además de decirles lo que tienen que hacer, hay cosas que la sugerencia ya está dada, ¿no? Entonces les facilita la decisión, ¿no? Simplemente les da la información necesaria, ¿no? A lo mejor son dos modos, NIRSpec y espectroscopía con NIRSpec o con MIDI, y para cada uno de los dos hay ciertas sugerencias, y ahí ya o viene el link o te dice un pequeño resumen de lo que se sugiere, ¿no? Entonces, desde luego, pueden seguirlo o no, yo recomiendo que sí, deben leerlo seguro.
Sí.
Acá en Inaue hay una duda.
Sí.
Sobre los targets of opportunity, veo que también puede entrar como tiempo discrecional, ¿no? De director. En dado caso, ¿cuál tendría mayor prioridad? ¿El tiempo que se asignó por target o por el tiempo discrecional?
Son dos cosas distintas. El tiempo discrecional es una cosa que pides en cualquier momento al director, ¿no? Lo juzga el director directamente, ¿no? Mientras que los TO son algo que tú pides en el Call for Proposal. Entonces...
Sí, pero supongamos
yo tengo la respuesta.
Una propuesta aceptada en esos dos casos, bueno, propuestas aceptadas en ambos casos, ¿cuál tendría más prioridad?
Yo sé eso porque he estado en los comités. Entonces, es más, me pasó alguna vez. Si tú tienes un target of opportunity para la próxima supernova tipo 1A que se ubique a tal distancia, etcétera, si hay tal supernova, tú tienes la prioridad porque ya tuviste el target of opportunity y el director discretionary time no puede entrar. Esas son las políticas.
Okay.
No, pero lo que dice Gloria es que si tú ya pediste una propuesta como TO
para esa ciencia
en particular, cuando salga la explosión, ese tiempo tiene prioridad sobre cualquier tiempo discrecional del director.
Si activa el
si se
TO.
activa, claro, si se activa dadas las condiciones.
Sí, hay una sección en JDocs de políticas de observación e incluye, por ejemplo, este caso, entonces, y varios otros. ¿Qué paralelos puedes hacer? La de la TOs, etcétera. Entonces, ahí pueden ver. Y la otra cosa que les quería decir es que ustedes pueden contribuir a mejorar todo lo que han visto a través del Help Desk. Si ven que algo de las instrucciones no es como lo dicen las instrucciones, entonces, por favor, no lo dejen pasar, hagan su trabajo comunitario, váyanse al Help Desk y díganles, miren, por ejemplo, a mí me pasó que en Firefox, cuando trataba de abrir el Pocket Guide, no abría con los Quick Links. Entonces, inmediatamente me fui al Help Desk y le dije, oye, no funciona, ¿no? Y ya me mandaron la solución y entonces lo probé, sí se solucionó, le dije a decía, ya funciona como tú me dijiste, y entonces meten la solución a una parte de Help Desk que se llama Knowledge Base, ¿ok? Entonces, sí.
¿Otra pregunta? ¿Aquí o externa? ¿No? ¿O alguien? Ahorita es un buen momento de que hablemos de estas dudas para empezar a hacer la lista de preguntas para el Help Desk.
Yo nomás comento que ahorita, por ejemplo, traté de instalar en el Observational Visibility Tool, o no sé cómo se llamaba, y no me funcionaba, les mandé un correo y en menos de media hora me contestaron. Está solucionado, ¿no? O sea, es bastante rápido.
Entonces, el Help Desk por lo general, y yo creo que conforme nos vayamos acercando a la fecha límite, dicen que tienen una respuesta, un tiempo de respuesta de más o menos 2 días. Entonces, ahorita a lo mejor no están cargados y te pueden contestar en media hora, pero sí que si más cerca de la fecha, pues bueno, seguro que van a tener más preguntas.
También hoy salió la nueva versión del APT.
Ah, sí. Eso, en mi opinión, se llama ironía. Ayer aprendimos a usar el APT y hoy aparece la nueva versión. Sí, lo sé. Solo eso, solo bromeo. Son cambios mínimos, sí.
Sí, hola, no sé si ya lo hayas apuntado, Aida, yo tenía esta pregunta.
Yo ya tengo 4 versiones.
Yo tenía esta pregunta de si querías hacer un joint proposal JWST-HST, ¿cuál era tu deadline? Sí, o los dos, o qué.
No, pero ¿en cuál de las dos?
Pero sí, pero si es un joint, es que se...
¿Qué puedes escoger? Manda la fecha de James Webb. Perdón, eso es culpa mía. Toma, Gloria.
O sea, puede ser cualquiera de las dos. O sea, ¿cómo defines? Es un joint HST-JWST. ¿Cómo defines si es una joint?
Es
una
igual como
HST
cuando
o
eran
un
joint
JWST?
HST Alma, joint HST Chandra. Entonces, tú metes la propuesta que es la principal y dices que también quieres el tiempo de telescopio de Chandra. Entonces, pero el deadline es del HST. Entonces, si te aprueban la propuesta del HST, por definición te van a dar el Chandra y los del observatorio Chandra se van a hacer bolas para conseguirte y ajustar el tiempo para que te lo den.
Aquí como es el mismo,
ya
STSI
ya
es
saben
el
que eso va a
mismo.
pasar.
No, pero o sea, es lo mismo, la misma política.
Los comités de evaluación van a ser diferentes y entonces lo que decía Gloria es que uno va a tener que decidir cuál es el caso científico más importante de las dos propuestas para que puedas hacerlo más fuerte. ¿Cuál es el que puedes hacer más fuerte? ¿El tiempo en James Webb o el tiempo en HST? Y creo que esa es la decisión basada en lo que acaban de decir. Es lo que entendí que fue la discusión.
Una pregunta.
No, pero vas a competir por el tiempo de un telescopio. Entras a competir por el tiempo de James Webb. ¿Tú ahora mismo qué crees que es más difícil? ¿Conseguir el tiempo de James Webb o el del Hubble?
Yo voy sí.
Sí. Pero yo nunca me han dado una joint proposal. Yo estoy usando razonamientos.
A ver, yo quiero preguntar, ¿cuál es la posibilidad de usar parallel observations en otras propuestas que que vayan a estar aceptadas o una cosa así, o lo que ya está? No sé si ya están saturadas o hay oportunidad de buscar y si sacar imágenes o alguna recomendación para...
No sé quién lo dijo, yo por lo menos lo he leído sobre por ejemplo, los IRC, se puede, IRS.
Sí, entonces serían paralelos usando observaciones del Early Release Science, me imagino. Entonces, la pregunta práctica es, ¿en dónde encuentras cuáles son las fuentes que se van a observar para tú saber qué paralelos vas a hacer o cómo?
¿Qué tan saturado está
el
sistema de paralelos?
Creo que, bueno, te puedes ir al roadmap de paralelos primero para saber qué combinaciones de instrumentos son posibles, ¿ok? Porque no todas son posibles. Ajá. Y luego, para saber las reglas, te puedes ir a las Science Policies de paralelos para saber qué está permitido hacer y no, para no afectar programas, etcétera. ¿Sí?
Sí.
Yo creo que hay que revisar los casos de las propuestas del Early Science Release
Sí.
Data, que
Los
están
targets,
todos
porque...
ahí, claro, con toda la información de los objetos y lo que están tratando de hacer para saber cuál es la observación que están haciendo y luego de ahí, basado en lo que dijo Aida de las policies, pues ver cuáles se aplicarían para los observations.
Decíamos que en un momento dado uno puede cargar el APT de esa propuesta y ver exactamente qué campo de visión van a observar en paralelo y si te interesa, ¿no? Tiene que ser que te interese el campo que está adyacente, ¿no? Tiene como muchas dificultades el modo paralelo, según lo siento yo, ¿no?
Pero al mismo tiempo es
aprovechar
el tiempo y quizás si se encuentran
un campo, un objeto que es de interés, pues podría ser más probable que te lo asignen, si es posible.
Sí, si por ejemplo se está haciendo una galaxia que está muy próxima, muy extendida y se va a hacer acá, a lo mejor te interesa.
Sí, claro. Yo
Sí,
no
sí.
tengo información de cómo han sido las asignaciones de las observaciones paralelas. Y no vi nada de eso. No.
¿no? El ejemplo que hay que seguir son, o sea, las políticas del HST seguramente van a ser parecidas. Por eso, en ese sentido, entonces los pure parallels, tú puedes meter una solicitud pidiendo parallels. Y ellos saben aproximadamente qué porcentaje del tiempo se vale o se pueden hacer los parallels. Entonces, se aprueba o no la propuesta y si alcanzas el tiempo te lo dan. Pero no creo que haya tal cosa como que se quede tiempo vacío paralelo, ¿no?
No, yo tampoco creo que pase que se quede tiempo vacío, ¿no? Seguro que aprovechan cada fotón que recibe el telescopio, de alguna forma u otra.
Entonces, les puedo leer la lista de preguntas que he ido acumulando para el helpdesk y si me falta una, me la dicen. Entonces, de todas maneras, apunté la de Rosa sobre el joint para aclarar perfectamente cómo va a ser. Sí es cierto que el joint HST web se manda al deadline del web, pero luego, ¿qué pasa si no te aceptan web? Pues no te aceptan tampoco el HST, ¿no? Pero lo podemos verificar. Tengo la de Parallels y ERS, por si quieren preguntar más detalles acerca de eso, Silvia. Tengo la de ¿qué pasa si uno manda a HST, el ciclo ahora en marzo, de puro HST, ¿ok? Y la imagen que la quieres usar para NIRSpec en James Webb, ¿ok? Pero como es difícil que te den tiempo en HST, también mandas un joint HST web, ¿ok? Y luego sí te dan el tiempo de HST, pero pediste un joint HST James Webb, entonces ahí como que no queda claro si les dices, oye, siempre ya no voy a crear el joint HST James Webb porque ya me lo van a dar en el ciclo normal de HST. Hasta ahorita no he visto ninguna restricción de si puedes mandar a ambas, ¿no? Te dicen, pues, si no quieres trabajar tanto, mejor manda un joint, ¿no? Pero tengo también la pregunta sobre paralelos y coronografía, ¿sí? Entonces creo que la pregunta es que si se pueden hacer paralelos con algún modo de coronografía, ¿no? Tengo la del problema de los visibilities en la nube de Magallanes, que si de plano no se puede hacer, es la pregunta de Gloria. Nada más, si me la redactas mejor, porque ahorita la tengo así escrita como para acordarme nada más. Está el problema en APT de que cuando haces load DSS no carga en Aladdin, pero necesito saber para que nos puedan ayudar el OS, qué versión de APT, etcétera. Exactamente qué es lo que más detalles para que ellos puedan ayudar, porque en algunas plataformas sí funciona. Déjenme terminar la lista, a lo mejor. Y Moving Targets Visibility Tool Not Working. ¿Esa quién me la mandó? Tengo Moving Targets Visibility Tool.
Yo traté de usar el Visibility Tool de Moving Targets y no me da un error. Y también Joel lo trató de usar y le da el mismo error que a mí. Entonces, sí que tengo toda la información ahí.
Necesito saber cuál es el
Yo le hago
error.
copy-paste.
Ajá.
No hubo problema para cargar el Aladdin. Esa pregunta quizás fue porque yo te la hice ayer, pero ya no hay problema.
No, aquí hubo bastante gente. A ver, levanten la mano el que todavía no ha resuelto eso.
Disculpe. No, era justamente que pienso que era un problema del internet porque justo después se regresó y pues eso funcionó. El load SDS sí funciona. Sí.
Ok, entonces cancelo esa pregunta, ¿sí? Ok.
Lo que ya no checamos es la página para checar duplicidad. En esa yo ya no me acuerdo qué página era, así que ya no lo intenté.
Es de MAST, el Data Archive, está en la presentación de Ancillary Tools y ahí sí que viene el link en donde en la parte de duplication. Entonces, si quieres intentarlo ahorita en lo que hablamos de las otras preguntas, y si no puedes, pues sí que lo agregamos, ¿ok?
Pero esa creo que es aparte del James Webb, ¿no? Esa es una página.
Sí, bueno, así 100% aparte no, pero sí que no es directamente con el Help Desk. Pero de todos modos lo vemos.
Pero la PT, ese sí está funcionando bien con Anadine, ¿no? Ese sí ya lo chequé.
Ok, súper. ¿Alguna otra pregunta? ¿Terminaste, Aida, de mencionar las preguntas?
Cancelo lo de duplicidad. No es una pregunta para el helpdesk, ¿correcto? Sí, entonces mi lista, pues ya, si hay otras preguntas, me las dicen.
Ahorita es su oportunidad. Vamos a tener a alguien en el del Help Desk dedicado a nuestra sesión para este masterclass. Entonces, si quieren, aprovechen, exacto. Podemos responder, nos podemos obtener respuestas a nuestras preguntas de una forma más rápida.
Acá surgió otra duda. Preguntan que si te dan tiempo con el James Webb, ¿cuánto tiempo es la espera para los resultados? ¿Te los dan una vez que te observan, te los dan inmediatos o hay un tipo de calibración o algo así que hagan para... Ajá, porque aquí yo decía que te los daban por mi experiencia con telescopios grandes, que así te los daban, y acá hay otros que con ALMA dicen que no, que tarda tiempo, entonces esa era la duda.
No estoy segura de entender la pregunta. Es decir, una vez que ya está funcionando el telescopio, que ya hicieron toda la calibración, que ya observaron IRS, que ya observaron GTO, me estás preguntando que cuándo,
¿Cuánto tiempo es
una vez que observan tu programa, ¿cuánto se tardan en darte los datos?
Sí.
Ok, eso no lo sé, entonces pues podemos preguntar. Sí, permíteme.
Lo de ayer de si hay planes para que en el ETC uno pueda meter un archivo FITS de una imagen de modelo o incluso un cubo de modelo y que nos calcule el mapa de signal to noise en lugar de andarle metiendo a mano estrellita aquí, elipse por acá y eso, ¿no? Ajá.
No creo que lo tengan para el ciclo 1, pero...
¿Alguna otra pregunta? Así, acá. A ver, ya llego.
Bueno, yo no he hecho la tarea de leer todavía mucho de la documentación, pero una primera pregunta que me ha surgido es si pueden darnos una pequeña explicación de cómo funciona el detector en cuanto a tiempos de integración, en cuanto a cómo acumula la lectura, qué tan rápido lo hace. A lo mejor eso sí se encuentra en una documentación, pero cómo puedes hacer uso eficiente de esa información para tus observaciones, para tu proyecto.
Hay una parte de detectores, así se llama detectores, en JDocs, y ahí explican el vocabulario que es particular a los detectores mid-infrared y near-infrared. Y hay también, para cada modo de observación, describen los readout modes y qué tan rápidos son o qué tan lentos son. Y como vimos ayer en el ejemplo de Omaira, hay una recomendación de usar un fast readout mode, pero ella ocupa el slow. Entonces, ese tipo de detalles depende del modo de observación. No me lo sé de memoria todos, pero está documentado.
Dicen prueba y error. O sea, en el workshop que fue Aida, hay un slide de la presentación del ETC que decía básicamente prueba y error, y entonces empezaba a dar una lista de cosas que pasan, ¿no? En este modo, si aumento los grupos, de pronto tengo problemas con los rayos cósmicos, en este otro modo ya no tengo problemas, pero en entonces el tiempo de integración recomiendo que sea menor que pero son como tantísimas recomendaciones una detrás de otra, que en realidad no hay como una recomendación clara, ¿no? Yo creo que es que no la tienen, ¿eh?
Y luego, pues sí hay que jugar con el ETC para tener la señal a ruido que tú quieres y minimizar el overhead cuando se pueda, ¿no?
Es que no podemos comer antes de las 2, así que les estamos
Pero
entreteniendo.
podemos hablar un poquito de cómo
No,
le
pero
vamos a hacer.
quería poner lo de la discusión científica. Exacto. Pero estoy esperando que me pongan el proyector. Es que no tenemos el input para proyectar, entonces, un segundito. Básicamente la discusión científica es a las 3, ¿no? De 3 Sí. Perdón. Sí, el helpdesk de 2 a 4 y de 4 a 5 y media la discusión científica. Y la vamos a hacer en 3 salas, dependiendo del área científica. Ahí viene, así que ya. Dejo de hablar. Por hablar. Todos son iguales. Sí. Sí. No, y James Webb tiene varios. Sí. Ahí está. Bueno, pues en cuanto a la discusión científica, esto es básicamente 2 transparencias para explicar lo que les estaba diciendo, que nos vamos a dividir en grupos y básicamente un grupo va a ser extragaláctica y cosmología y las chairs vamos a ser Aida y yo. Y aquí va a ser a galaxias y cosmología, así que aquellos que estén interesados en ese área, pues directamente se quedan acá. Y luego, pues en cada una de las sedes, en el auditorio principal. En las sedes hay muy poquita gente ya, así que como hemos acordado con ellos que en teoría íbamos a hacer paralelos también con ellos, pero hemos acordado con ellos que todos van a ser extragaláctica y cosmología, hasta donde yo entiendo. Y si ese no es el caso, pues que nos avisen, pero me consta que el iría sí, no sé qué.
En el INAOE no sé
En el
si
INAOE,
quieren
mi duda.
conectarse nada más a la parte de extragaláctica y cosmología o quieren conectarse a una de las otras dos. De todos modos, tenemos la capacidad
Se puede
y
hacer.
las sesiones y ya están. Nada más que, pues, nos gustaría
Está
saber.
el link de Zoom para cada sesión, y solo que no sabemos si la ocupan.
Exacto, y si no lo ocupan, pues ya. Pero es más fácil no hacer 3 teleconferencias y si no hace falta, pues no hay que hacerlo.
Después hay otra de... ¿Perdón?
Aquí somos muy pocos, entonces preferimos que sea la de extragaláctica y cosmología.
Eso es lo que tenía entendido.
Perfecto.
Sí.
Entonces, la otra es medio interestelar, va a ser en el aula 1 y el chair es Roberto Galván, que está allá al fondo.
Te puedes levantar para los que no te conocen.
Le dije, en el INAOE, en caso de que haya alguien interesado en cosas no extragalácticas, dado que tienen un link de Zoom, pues cualquiera se puede conectar desde su laptop, ¿no?
En realidad, sí.
Entonces yo creo que
Sí.
lo pueden mandar y ya. Ajá.
Claro.
Ajá.
Ellos tienen el link, hasta donde yo sé, se los mandé justo antes del evento, ¿no? De cada sala.
Entonces, ¿pero se conectarían por Zoom o se conectarían por Skype?
Todo es por Zoom.
Ok, entonces yo le mando el link a la persona interesada y que se una.
Ahora explicamos lo del Skype.
Ese es paso número 2.
Ese es el paso número 2. Y entonces estrellas, física estelar, planetas y astrobiología, gracias a Vero que había puesto astrología, no sé por qué. Y me lo...
Entonces...
No va a haber astrología, ya se me van todos de la sala, ¿no? He perdido el interés.
Esto es la organización para lo de del science, ¿no?
Sí, las discusiones científicas.
Claro.
Y entonces, eso va a ser en el auditorio viejo.
Ajá.
Ustedes saben dónde es, yo
sí
no.
Sabemos dónde es.
Y la chair es Gillen.
Yo.
Entonces...
Por donde está la meteorita.
Vale, entonces esto es una sugerencia de cómo organizarse una vez estén en cada área. Lo que vemos es que, de nuevo, pues es clave el modo instrumental que uno quiere usar, ¿no? Entonces, los chairs van a preguntar en la sala cuántos hay interesados en cada uno de los modos. de manera que se pueden hacer pequeños grupos de discusión a ver si encuentran un objetivo común, se quieren hacer fuerza conjunta. Yo me encargo del ITC y tú de la PT o algo así, ¿no? Sí, por supuesto, si el número es pequeñito de gente, pues directamente la discusión es sencilla. La previsión era que, por ejemplo, Extragaláctica y Cosmología tenían inscritos en ese área como 40 personas, entonces sentíamos que 40 personas hablando no era una discusión realmente para concluir algo y por eso lo quisimos dividir en pequeños grupos, pero desde luego ese es a vuestra consideración.
Bueno, el punto de esta discusión es que nos vayamos de aquí con una idea, al menos de personas o de modo de instrumentación o de ciencia que queramos hacer para mandar una propuesta a James Webb. Entonces, aprovechando de que tenemos a gran parte de la comunidad aquí o conectada, entonces queremos que eso dé lugar a este tipo de discusiones que no puedes tener tan fácil por correo. Entonces, ya sea yo tengo una fuente o yo quiero usar esto o yo tengo un science case porque siempre he querido contestar esta pregunta y no he podido a la fecha y James Webb puede. Entonces, ese es como el objetivo general de esta sesión, que tengamos ese espacio para realmente discutir. Hasta ahorita fue un montón de cosas técnicas y prácticas, pero sí que nos gustaría que salieran con un poco más de discusión científica.
Claro. Y luego, solo consideraciones. Una es que si al final se hacen subgrupos y ustedes están interesados en varios modos, modos de observación, siempre pueden estar un rato en uno de los grupos y moverse al otro. Si están interesados en distintas áreas, también están libres de moverse durante la hora y media que dura el evento. Y la otra cosa es intentar involucrar lo más posible a los estudiantes y a los jóvenes investigadores en la discusión y invitarles a participar en la medida de lo posible. Y eso es todo lo que tenía yo.
Entonces, a las 2 es la comida. Me pidieron que no llegáramos antes. Entonces les paso el dato. Vayan a por agua, al baño, lo que necesiten en unos 15 minutos y luego ya vamos a comer. Y después nos vemos a las 4 en los grupos. Ya nos vemos en los diferentes lugares. Sí. A las 4 pues nos vemos en las discusiones. ¿Apuntaron todos el salón o necesitan que lo volvamos a poner? Ya, lo apunto.
Oye, Omar, y después de las discusiones nos volvemos a reunir aquí, ¿no? Después de las discusiones, no se vayan, después de las discusiones nos volvemos a reunir aquí a las
5:30.
A las 5:30
nos
para
vemos
la
de
clausura.
regreso. Obviamente aquí de 2 a 4 vamos a tener lo del help desk, ¿ok? Entonces, vayan a comer, piensen en las cosas que quieren preguntar y vuelvan aquí. Va a haber alguna de nosotras que vamos a estar manejando lo del help desk para que todos ustedes tengan tiempo de preguntar, además de las preguntas que ya apuntó Aida.
Aquí ya nos confundimos. ¿Van a ir a comer de qué horas a qué horas?
De 2 a 4, pero también es el tiempo del help desk.
Ok.
¿Sí?
Ok. Y entonces, de ahí es cuando se dividen para a las 4.
Ajá. Y a las 4, de todos modos, a las 4 nos conectamos a través de esta misma conexión con ustedes para que estén en la sesión de Extragaláctica. Con el INAOE, ¿sí?
Súper. Ok.
Ahí está la novela.